Hello everyone and welcome to this course on linear algebra. So basically linear algebra is just a branch of mathematics where you deal with the various mathematical objects called vectors and their transformations. So first let us start what vectors are. So the fundamental root of all the linear algebra are the vectors. So vectors are the building block of the algebra that you say. So what are the vectors? So there are three different perspectives from different discipline of the sciences. One is the physics perspective, what vectors are. Second one is the computer science. And the third one is the mathematician perspective. So since all you are from the physics background, so for physics a vector is simply, what is physics? What is vector for a physics students? So for physics the vectors are arrows pointing in space, and what defines this vectors is magnitude, what you call as the length, and the direction in which it is pointing to, right? So only the magnitude and the direction defines a vector for a physics students, and unless these two things are same, you can move this vector anywhere around the space and it will be the same vector for physics, right? You can take it at one place or move it, transport to the other place, it will be the same vector if the direction and the magnitude is the same. Okay. For a computer science perspective, a vector is simply an ordered list of numbers. Okay. So it's just like a list of numbers, but the list has an order in it. For example, suppose a computer science students studying some space or some objects by having say three different properties, say length, breadth and height. So for them the order matters. Length should come first, breadth and height. If you change them, it will have a very different meaning. Okay, for example, take example of suppose he studied the house prices and the area. So if you have area and the prices, if you interchange them, it will have a very different meaning other than this. What defines the dimensionality of vector in physics is in what dimension you are constructing these vectors. For example, you can construct in 2 dimensions, so it is a 2-dimensional vector. If you construct them in 3 dimensions, it will be a 3-dimensional vector, right? But for a computer science perspective, a vector is the number of components in the list. So if you have 2 components, it's a 2-dimensional vector. If you have 3 components, it's a 3-dimensional vector, right? And I'll come to the mathematician perspective, which is sort of generalize both of these ideas. They say that a vector is a mathematical object unless it satisfies two properties, which is vector addition and the multiplication by a number. So I'll come to that very mathematical definition when we first define the vector spaces, but let us stick with these two perspectives. And these two perspectives, although they seem very different, this is a geometric perspective, right? It defines a vector purely based on the geometry. This is an algebraic perspective. It defines a vector based on certain numbers, right? So these two perspectives, they seem very different, but they are very closely related. They are the same idea. They are talking about the same thing, but only in a different way. Okay, and we will see how these two perspectives are the same one. That is the first thing we will do that. Okay. So in linear algebra, usually we treat a vector as an ordered list of numbers, which has a geometric meaning. That is what linear algebra comes into picture. So we have a vector as a list of numbers which has some geometric meaning. Okay. In physics, the vector can start anywhere in space. Okay. You can have a vector at any point in space. But in linear algebra, when I say a vector, it is assumed that it originates from the origin. It cannot be anywhere in the space unless we specify them that it is from this point to this point. But in general, if I say a definition of a vector, it is from the origin, not from any point of space. Okay. So these are the two things. So let us first define vector comes with different characteristics. First characteristic is dimensionality. And the second thing is orientation. These are two different things that you can think about a vectors. For example, suppose I defined a certain list of numbers. Say y is 2, 3, and say z is. So I define these three vectors, right? So the first vector, if I say it has 4 numbers, so its dimensionality is 4, right? The second is also have 2 numbers, its dimensionality is 2. So I say that this vector is in R4 space, which what I mean is, so this is a set of real numbers and this is the dimensionality. So all the numbers which are contained in is from the real set, and they are the, means I need the 4 pair of numbers to define this vector. So this n defines the dimensionality. So this x belongs to a R4 space, means it is the set of real numbers with dimensionality 4. So I need 4 numbers to define this vector. Okay. For this will be R2, because I need 2 numbers and this is a 2-dimensional vector, right? I need 2 real numbers to define this vector. Okay. Similarly, this is how much? R4. Okay. But what is the difference between these vectors? So this is what we call is as a column vector, and this is a row vector. Although these 2 vectors, they look exactly the same, but fundamentally they are different. They are different because they have a different orientation. Okay. It is a row vector, it is a column vector, this is a row vector. So fundamentally they are, although they have the same numbers, in terms of information they are the same, but in terms of the orientation they are different. In linear algebra, the operation that this vector can perform and the operation that this vector can perform are fundamentally different. Okay. They are not same in linear algebra. In linear algebra, the vectors are usually treated as a column vector unless we specify that this is a row vector. If I say a vector in linear algebra, it is mean that it is a column vector by default. Okay. Is this definition clear? So this is just some building points that we have in linear algebra. So in linear algebra, whenever I say a vector, I say a column vector. A column vector means it has certain list of numbers. If I say a vector of 3 dimension, it means it has 3 numbers. Okay. In linear algebra, it cannot only have numbers, it can also have functions, but that is a very broad area. We will not deal with such vectors, but in general you can have anything in between these. A can be a function, like you can have 3 different functions, a vector of 3 different functions, fx, fy, fz. Okay. But in general now for this course we will deal only with the numbers. We will not take the vectors of the functions. Okay. So this is a very basic definition. Now let us relate how these 2 ideas of a vector, which is a geometric, and the numbers are related. Okay. So to compare these 2 ideas, let us first consider. Yes. Oh, sure. Okay. So now we will try to relate the idea between computer science and the physics perspective. Okay. 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 So in order to do that, let us first consider a space, and in this space, suppose we are in a 2-dimensional space. So we have an horizontal axis, let us call this x, a vertical axis, let us call this y, and the point where these 2 axes meet, we call it as origin, right? And this is the starting point of all the vectors in linear algebra, right? And suppose I define a vector, say 2, 3. Okay, so how I define this vector inside this centimeter, meter, whatever you want to have, and certain other measurements on the y scale. So what these numbers specify is how can I get from the origin to the head of the vector. So how can I get from the origin till the tip of this vector. So it's like a movement. So what this specifies, I should move 2 steps along the x-axis and 3 steps along the y-axis. So if I move 2 steps along the x-axis and then 3 steps along the y-axis, the point where I reach, if I draw a line from origin to this point, this is my vector v. Is it clear? How to draw a vector. So these numbers simply specify the instructions how you get from the origin to the tip of the vector. Is it clear? So it's like movement of 2 steps along the x-axis, 3 steps along the y-axis. But what does the negative implies? Suppose I want to draw this vector minus 2 times 3. How to draw this? It's very simple, because this is movement towards the positive, this is movement towards the negative direction. So you move 2 steps towards the left and 3 steps up. So this is your W vector, this is your V vector. Okay? Okay. So this is simple connection between these 2 ideas. They are essentially the same ideas, only one is the geometric representation, which is the physics. The other one is the algebraic representation, which is the representing vector as a list of numbers. Now from this construction, you can think of that for each point in space, I can draw a vector, right? So each point in space represents a coordinate for a vector. I cannot draw 2 vectors for one point, right? Can I draw? For this point, can I draw 2 vectors? No. I can draw only one line, right, from here to here. I cannot draw 2 lines. So it means every point represents one vector, and conversely you can say that each vector is represented by only one coordinate system, right? If I define V, it is only 2, 3. I cannot define it in any other way. It cannot be 3, 5, because it will be a very different vector. Okay? So there is a one-to-one correspondence between the line and the numbers. So that's why they are the same. Okay? Is it clear? Now these vectors, they are just like some objects lying in the space. What these vectors do is what we study in the linear algebra. So we study the operations, okay, or the action that these vectors perform, and the action that these vector performs, we call them as operations. So what are the very basic operations? Addition. First is addition. The other one is, what is the other operation? Multiplication, right? So we have 2 operations, addition and multiplication. So we have addition between vectors and the multiplication by a number. Okay, so we will study these 2 operations. These are the very basic operations, and all of the linear algebra is dependent only on these 2 operations. Like most of the linear algebra, if you understand these 2 operations, it is the full essence of the linear algebra. You will not go beyond these 2 operations. Okay. So let us first start the vector addition, which you might have done before in some way or another way, right? So let us again start with some axis, y and x, and I have defined 2 vectors. Suppose this is my vector 1 and this is vector v, and suppose I have another vector, say w vector, and I want to define something called as v vector plus w vector. So what will this be? So we will study this vector addition in terms of both the perspective, like computer science as well as the physics, how they are related. So in physics, what you do? You take this vector, parallelly transport it so that the tail of this vector lies on the head of this vector, right? So this vector you parallelly transport, so you make it like this. So this is your w vector, and then you join the origin till the tip of this vector. This will be your v plus w, right? This is how you do in physics. Yes? Now how to understand this vector addition physically? Like what is actually happening when you do this? Why this works? Why only this type of, like, why transport it to this point, not any other representation, or not like I can move it, maybe rotate it and put it? Why not that? Why parallelly transport it and like draw a line which joins the tail of one to the head of one? Why this representation? So it's very easy if you understand this in terms of the movement in space. Okay. So like I told you before, what does these numbers tells you? These number tells you how you move in space to reach that point, right? From the origin, how you reach to the head of the vector, right? So you move 2 steps and then 3 steps, right? You reach to the vector head. Now consider the addition in a simple way of 2 numbers. Suppose I have these 2 numbers, how you add them? So the basic idea is you construct a number line, then you first start 2 steps, then again start 3 steps, and the point where you reach is the sum, right? So it is like 2 steps and then 3 steps, the total is, the point where you reach is 5, right? That is how the addition works. Similarly, in this case, what you do is, let us take an example. Suppose my v vector is same, v vector is same say 2 3, and take w vectors maybe like 1 3, something like that. Okay, now I want to add this. So the first thing is, you can think of this as the movement in space. So I start from this point, I move 2 steps right, and then I move 3 steps up, so I reach this point, which is the first vector, right? Now from this I again start this movement, so which is, I start one movement here and then 3 steps up somewhere here, right? So this is the final point from here to here, right? This is how you study. So basically what you are doing is, you are moving along the first vector, then you are moving along the second vector, right? So basically what is your net movement along the x-axis? It is, first you move 2 steps, right? Then you move 1 step, right? Maybe let me draw it clearly. So this is v, this is w, this is v plus w. Okay. So you move 2 steps, then 3 steps, then you move 1 step, then 3 steps, okay, and you reach the final point. So the total movement along x-axis is 2 plus 1, right? So v plus w, your x movement is 2 plus 1, and your y movement is 3 plus 3. So this is how you define. So you can say that 2 3 plus 1 3 will simply give you 2 plus 1 and 3 plus 3, right? So what you do is, you just add the x movements and just add the y movements, you will get the addition of the vectors. Okay, it's quite straightforward how you do it. And similarly you can define the subtraction, just subtract the x movements from the first, y movements from the first, and you will get the subtraction. Okay, so this is the vector addition. What is the multiplication by a number? So just multiplication simply implies that you are changing the length of the vector. Okay, so if I have a vector v, if I multiply it by 2, it means now my length should increase by 2. Yes, if I make it half, my length should decrease by half. So if I have a vector v, so 2v simply means that my multiplication by it simply means that for this vector, so v is 2 3, 2v simply means 4 6, right? Okay, so what are these numbers doing? These numbers, they are scaling the vector. They are either making it bigger or they are making it smaller. They don't change the direction, either you make it like this or you make it smaller, right? They are scaling the vectors. So that's why the numbers, they are called it scalars, because they scale the vectors, right? So you have these numbers which are called as the scalars. So this is the mathematical and the geometric perspective of what multiplication and the addition is doing. And this is very core of the linear algebra. Only these two operations are required in order to define any other operations. You will not go beyond that. Okay. Now let us define something which is called as the vector coordinates. What these numbers basically imply. Let us then define this. Okay. So let us go to this n. So any vector. So let us take this v to be 2, 3, right? Let us take this example. So you know that what this number will do. It will rescale any vector by twice of its amount, right? That is what we study in the previous. If you multiply any vector by 2, it will make it twice the length. If you multiply it by 3, it make it 3 times the length, right? So there is a very interesting way of thinking of these two numbers as it scales something, right? So suppose I go to my original coordinate system, and in this coordinate system I have something called as the unit vectors, right? So you have heard of this I and j cap, right? What are I and j caps? They are the unit vector in x direction and unit vector in y direction, right? And they are typically, we specify them as 1 0 and 0 1, right? Is it clear? Why 1 0? Because I only step, like if I take them as the coordinates, so I only have to move along the x axis by one step, right? That is what this I vector I cap define, that I need to move only one step along the x axis, not in the y axis. So that's why the y component is 0. For this j vector, I only have to move along the y axis, not in the x axis. So that's why the x is 0. Is it clear? So now this vector v, I can write it as 2 times 1 0 plus 3 times 0 1. Is it clear? So any vector, what it does, it just I can represent them in terms of these unit vectors. It's just the rescaling of the unit vectors. Okay. Is it clear up to this point? Any question? Any questions? So what are these numbers? The first number, it rescales the unit vector I cap. The second number, it rescales the unit vector j cap. So v simply I can write as 2 I cap plus 3 j cap, right? Yes. So what these two do? It rescales the unit vector in the I direction, 3 rescale the unit vector in j direction. So that is what this component implies. These components simply implies that if I am in any space and I have some unit vectors, so in order to define this vector, I have to rescale that unit vector along the I axis by the 2 factor and along the j axis by the 3 factor. Then I'll get this vector. And this combination, we defined it as a linear combination of 2 vectors. Okay. Is it clear how we define the linear combination of these 2 vectors, right? So this is a very basic definition, but you can ask me why I choose I and j cap. I can choose any other vectors. What is so special about I and j? Yes or no? I can choose any other vector. Suppose I can choose, suppose maybe a vector and b vector. So I can still write some maybe how say alpha and beta of, I can still write that. That is not a problem. Okay. So still it happens, but let us make it more generalized. Instead of using these I and j cap, let us use a generalized way of defining these vector components. Okay. Is it clear up to this point? I think it's very basic, so you might already know most of it. So right now we have defined the significance of the vector components and how to define a vector in the space. So we have defined 2 things: how to define a vector in space and what is the significance of the vector components. Okay. Now in general, let us choose any two scalars, say A and B. These are the two scalars. Scalars means they are just the numbers. It can be any number, 1, 2, 3, 4, 5, whatever number you want to choose. Okay. And let me define a new vector, u vector, as a linear combination of two vectors of A v cap plus say B w cap. Okay. Now I don't choose I and j. I choose any two vectors. Okay. Can I able to define a v vector v based on the two different vectors? Okay. Is it possible? Is it possible or not in two-dimensional space? Okay. So let us see. So let me give you a very basic. So in this case, what this means? If I have a vector v, I add a vector w to it, right? Something like this, and this is A, this is B, right? So what this means is I can make the length of this vector be bigger or smaller, right? By changing this B. The w can be very big or it can be very small, right? So I can, if I fix this, which is A times V, I am fixing it, right? So I am changing only B times w. So w is fixed, I am changing only the B. First the vector is only this height, now I make it twice bigger. So now I can go to this point, right? If I make it 3 times bigger, I can go, so I can move anywhere along this line, right? If I only change B. Yes or no? Yes. Similarly, let me do this. Suppose I only change A. Oh, let me keep it here. I only change A, keeping B fixed. If I only change A, I can move only along this line, right? Yes or no? So it means that if I fix only one variable, the other is a line. I can move anywhere in the line, right? So that's why we call this as a linear combination, because if you fix one, the other one can give you a line. Similarly, like you have y is equal to mx plus c. You fix one, change only one variable, you can move along the line, right? Okay. So, but the so far is you can move along this line. But what happens if I change both? I can move to this point, to here, here, here. I can move anywhere in space if I change A and B, right? Can I move anywhere in space if I change A and B? Yes. So I can move anywhere, means any vector. By taking two vectors, I can make any vector in space. So this choice of I and j is not unique. You can take any two vectors and you can construct a third vector by just rescaling those two vectors. Okay. The only point when it is not possible is when these two vectors are parallel. If v and w are parallel, then you can just move along a line. Yes or no? Because you can just rescaling it. You cannot move apart from this line. What are the other possibility when you cannot go? When you cannot go through full vectors, full space, is when one of the vector is 0 or both of the vector are 0. Then only you can move along a line or a dot. Suppose both the vectors are 0, like it has 0 0. Say v is 0 0, w is 0 0. So you will always be here. You cannot move anywhere in space, right? Whatever number you choose, you will always be 0 0, right? But if you take to be 1 2, then you can only move along this line. Yes, you cannot go anywhere in space. So this linear combination, so how many vectors you can get by this linear combination defines the span of these two vectors. Okay, spans means what are the possible vectors, all the possible vectors that you can get by this linear combination. So that is what is defined by the span of this. Okay. So if you have two vectors in space which are not parallel, which are not linearly dependent, that is, I'll define the linear dependence a little bit later. But if you have two vectors which are not parallel and which are not 0, you can span the full 2D space. Yes or no? You can go to any point in 2D space. So you can get any vectors in 2D space using these two vectors only. So this is what I define by the span of the vectors, okay. And span is simply the all possible, let me define.
So should say the span of the U and V?
Yeah, span of U and V. Span of say W and V and W is the set of all THEIR, they are linear combinations. This is a very basic definition. It's not a very mathematical definition, but just for your understanding, okay? Yes?
V and W
Are the two vectors which
and they must do particular.
it can be anywhere. It not be the only thing is, okay, you can take them any perpendicular, non-perpendicular, parallel or not. So let us take the case when both are parallel. Both are parallel means suppose V is 1 2 and W is 2 4. Now they are the same line. Like if I draw it on space, so V will be this point and W will be this, like this point. Now what is the span of this? Where you can go in space? You can only go along this line. You cannot go beyond this line. So span of this is only the line, because you can get all the vector in this line, you cannot go beyond this line, okay. So this is the span.
So when it's span, it just remind me of the car sweeping span for the front window.
Oh, it's the same thing.
But then the radius is fixed, so it can't go.
But if the radius can change,
Yeah, that means
but it can sweep the circle. Yeah, it can sweep the circle like this. It can go to full space, right? In some sense. Now this is the example of a 2D span or 2D. Suppose I have a 3D space. Okay, in the 3D space I only have one vector. What is the span of this vector? In 3D space, if I take only one vector, what is the span? Oh, or let us take in 2D space, if I take only one vector, what is the span of this vector?
So the line.
It will be the line, because the only thing I can do is I can make it bigger or smaller. So if I make it bigger, I can go it to this infinity, or if I make it minus bigger, like minus infinity, it will go something here, right? So I can go to any vector along this line. The span of one vector in 2D is only a line. Yes. The span of two vectors in 2D is, if I take another vector, say this vector and this vector, if I take these two vectors, so what is their span? They can go anywhere in space. If I make it very big and very small, I can go to this point. If I make it very big, I can go to this point. Yes. So the span of two vectors which are not parallel is in 2D is the full space. Yes. Now go to the 3 dimension. If I have only one vector, I can go to a line in 3D space, right? If I have two vectors, then I can go to a plane. Like if I have two vectors, like suppose this room, I define two vectors, one is along this axis, the other one is along this axis. Okay, so where can I go? I can sweep the full blackboard, but I cannot come out of the blackboard. I need to come out of the blackboard, I need an additional vector. So in 3D, you need 3 vectors to span the full space, at least 3 vectors. But there are conditions when you can span the full space. The first condition is they should not be 0. The second is they should not be parallel, they should not be linearly dependent. That is what we define. Okay, so we define the linear dependence from the from this concept. Okay, so is the span clear? So what does, so you can think of this as the two vectors in the 3D spans a plane, right? What the third vector do is move this plane along the third axis. Okay, so you can so the choice of the vectors is like we use these I and j. It's not very unique. You can choose any vector and you work with it. Okay, is it clear? Any question up to this point? No? That's very good. I'm a great teacher then if you don't have any question. Okay. So, from this you can define the linear dependence, that if the span, suppose in 3D you have the two vectors which have some certain span and you add third vector to it. Okay, if the span does not change, then what is the reason when the span does not change? So I have.
What do you mean by saying the span doesn't change?
Span does not change means the possibility of the points in space that I can reach with those two vectors is still the same, so even if I.
Span is a property.
Span is like, it's like you can think of as like what are the vectors I can get from these two combination of these two vectors. So in 3D space, suppose I have three-dimensional space. So the span of this and the span of C, say U, both have the same span. If I say both have the same span,
U is 0.
no. If I say no, U is non-zero, that is also given.
So that is a paragraph of.
It means that what does this specify? It's a plane in 2D, right? In 3D this is the plane, right? This span is the plane in 3D, right? So what this implies is I'm not going out of this plane even if I add third vector.
C is 0?
No, C is not 0. It means U is contained in this vector. U can be represented by the combination of these two. Yes, U can be, if I can represent U as a combination of these two, I cannot go out of the plane. Like if I have these two vectors and I define a third vector which is like this, still I cannot come out of the plane because I can represent this third vector as the combination of these two. So that's why my span does not change. Is it clear? So it means that this defines, if there is no change in span, it defines that the third vector can be represented as the combination of the first two vectors, right? And this is how you define the linear dependence. So it means that this vector U is already contained in the span of these two. So it means U depend on these two vectors. U depend on these two vectors. So U is dependent on V and W. So U can be represented as some combination of A prime V plus some B prime W, right? This is what it means. If I say that it is still in the plane, is it clear? So this is how you define that U vector is linearly dependent on these two. Okay, but suppose you have a third vector, so this span will be changed. So there is an increase in spans if you have the third vector, means the third vector does not depend on the first two vectors. Then only you can increase your span. You can think of it as how far I can go in space. Okay, so if I have only two vectors, I can go like around this blackboard. If I add third vector, can I go beyond this blackboard? Then it is not linearly dependent. If I still remains in the blackboard, then it's linearly dependent. Okay. So and from this we defines the basis. Okay, you have heard the word basis. Basis is the set of the linearly dependent vector which is used to span the full space, like which can span the full space. That is how you define the basis. It is the linearly independent vectors by which you can get the full space. So in 2D you need at least two vectors, right? Because only by combination of two vectors you can go to the full space. So in the basis of two-dimensional space will at least have two vectors. In three-dimensional space, you will have at least three vectors, right? So that is three-dimensional vectors. That is what I mean. Okay. So this is a basic idea about the normal space and how you make the use of it and what are the spans. Like this is very basic that you should know in order to go into the vector spaces. Okay. So now let us go to something is the transformation of the space. How we can transform the space. Okay. Okay. Should I continue or you need a break?
Yeah, you should have a break.
Okay. Okay. So yes.
These two basic vector is not necessarily the perpendicular.
It's not necessarily any. They should be independent. That is the condition. They should not be orthogonal, but the definition of basis is they should span the full space. They should be linearly independent and span the full space. That is all it is required. You can have like in this case you can have 0 0 and you can have 1 1.
So this span thing is a bit more generalized than when you say orthogonal. And orthogonal is more generalized than saying orthonormal. So the span
The big one.
so this is a more general case.
Okay.
Bit larger set of. Okay.
Usually orthogonal means that they are linearly independent.
Okay.
Yes.
You want some questions?
Yes.
I mean, only one exception is parallel.
No, parallel and 0. If one vector is 0, means that is the point in space. It's located at the origin. So you cannot go beyond the origin, right? So these are the only two conditions. Like the in 3D it's more general, like you cannot make it combination of the other two. Parallel, what does parallel means? Parallel means you can represent one as a scale factor of the other, right?
What I mean was, they say that it doesn't need to be orthogonal, but if it parallel is not linear combination.
No, parallel means because if I in 2D, if I say V is parallel to W, but basically what this means is you can represent V in some scale factor of W. So it is indeed not a linear combination, but you can think of it as a linear combination because it is like W is represented as some A times V.
It's just other case.
Yes, because it's only one vector. So, but you can have like if you want to represent, you can have some B times 0 vector. Then this is a linear combination, right?
Okay, which
Means it's still a linear combination.
linear combination means two vectors.
Yes. Yes.
But this is just one vector.
Yes. It's a scaling, but still it's a combination. Like you can. What I mean by linear combination is, can you generate the other vector from the first vector? Like given the vectors, can you generate any additional vector? So if you have two vectors, the linear combination will generate a third vector, right? If you have only one vector, you can generate multiple vectors by rescaling it. So the generation of the vector, that is what I mean. Okay. So I hope the last lecture didn't kill you. So let's move to the next lecture. And I hope it's not too difficult because it's only transformation. And transformation is just a fancy word for function. So in normal sense, you have a function which takes some input and give you some output. Transformation is the same thing. It simply takes some vector, input vector, and make something with the vector. It do something to the vector, so you get an output vector, you have an input vector, apply some transformation and get a output vector. So it's just like that, okay. So a simple way you can do is like, suppose I have a vector and after transformation, suppose this vector goes to here. So this is a transformation, okay. So the thing is your vector gets changed, okay, after the transformation. But how to understand this transformation? So a simple transformation is you can rotate a vector, or you can make it another transformation is you can make it bigger or smaller. That is also a transformation, right? You can take a vector, make it twice of length or half of its length. That is the transformation, okay? So how to understand this transformation mathematically or physically, okay? Now, in order to do that, let us consider that what transformation do is not only to a vector, it does something to the full space, okay? So in general, what transformation do is it takes every point in space and do something to all these points together, okay? It does not do only thing to the vector, but it do something to every point in space, okay? A simple thing you can think of is like, suppose I have this sheet of paper, okay? I'll make it again. Oops. Suppose my space is this, and what my transformation do is
just break the sheet over.
Yes, and my transformation do something like this. So the full sheet get transformed or get rotated, right? It's not only one vector, but the full space is get rotated. So this is one kind of transformation. What I can do is I can take this sheet and move it like this. This is also a kind of transformation. Or I can do is something more very complex is I can take this and roll this sheet. This is also a transformation, okay? But all of these transformations are different kind of transformation, okay? In linear algebra, because it's linear, we only deal with the linear transformations. We will define that what linear transformation means it, but basically what physically it means is a line. If I have a line in space, it will always be a line. Oh. It will always be a line. So even if I transform this like this, so all the lines are always the line. But if I transform like this, so the line now become curve. Yes. So this transformation is not a linear transformation, but this transformation is a linear transformation. The other thing that the second point is the origin should be fixed. You cannot change the origin. You cannot change the starting point. If the origin gets shifted, for example, if I move it from here to here, I am shifting the origin, right? So that is not a linear transformation. So these are the two basic ideas that you should think of when you think of the linear transformation. First, a line should remain a line and the origin should be the same. Okay, this is only the intuitive. Mathematically how to define it, we will do it maybe tomorrow, but this is only the basic idea about the linear transformation. But what exactly it means a linear transformation, okay? So let us mathematically and physically do about a linear transformation. So what I mean is, suppose you have a vector, okay, and I say this vector is say -1, 2. So how to draw this vector? It goes -1 here and 2 here, right? So this is the vector. Is it clear how to draw this vector? It's minus on the x-axis, like go left 1, go up 2, okay? Now what I do is, suppose this vector under the transformation changes to some other vector. It can change to this vector, this vector, this vector, any other vector it can change to. There are many other transformations, right? So so let us think of this vector v. I can represent this as minus I cap plus 2j cap, right? In the original system, I represent this as minus I cap plus 2j cap. That is the original statement, right? I can represent this as a linear combination of my basis vector. Now after the transformation, v vector will change, but also I and j vector will also change, right? But these are the vectors, because my full space is getting transformed. If I rotate it, everything gets rotated. So v will get rotated, I will get rotated, j will get rotated, right? But one thing will still remain, that my new v vector will be minus I of nu, or maybe I prime cap plus 2j. This still holds, because the line will always be the line. You are not changing that because of that property, right? You are not doing anything, you are not making it curve. So you just have to find out your new I cap and new j cap. If you find it your new I cap and new j cap, you can find your new v. That is all you have to do. Is it clear?
But new v is still the same v, right?
No, it will be in the transformed v. If I rotate it.
mathematically it look different.
Yes.
Geometrically.
Yeah, geometrically it will be the same. It will be the still in the same. Like suppose I rotate everything by 90 degree. Okay. So my vector will be here. If I rotate it by 90 degree, it will be something like this, right? So
this is your transform vector or
this is my original. This is transformed. But when I make the transformation, my full space getting transformed. My I is getting transformed, my J is getting transformed. My basis vector is also getting transformed. That is what transformation do. So suppose I have a transformation which transform this space to some other space.
you transform both, right?
I am transforming the space. If I transform the space, it means that my I and J are also getting transformed. Yes. So I am like, for example, I take this blackboard. If I rotate it by 90 degree, so all the content of this blackboard will get rotated, right? So this content means it is, what are I and J? They are inside this space, so they will also get rotated. That is what I mean by transformation. I am transforming the full space, because I and J are not unique. I told you before. You can form any other vectors. We can define the space. You can form many bases which can define the space. So everything will get rotated. Okay. So let us take an example. Suppose suppose my I vector, okay, goes to, say, the new point of my I vector is 1, -2. For my J vector, the new point is say 3, 0. Suppose I make this transformation. It means that my original I, which was 1, 0, right, and it is 0, 1. So this is my original I. Now I change my space so that the location of my I is now this. Okay, is it clear? And the location of my J is this. If I know this, because this is the thing that you should know. When you transform it, I assume that you know this. Okay, and later we will find out how to find this. We will do later, but for now, let us assume that you know that your I, which was this, now it goes to this. Your J, now it goes to this. That is, you know, that is given. Okay, so what will be your new V? It use the same formula. It's like minus of 1 -2 plus 2 of 3, 0, right? Is it clear? Because your V will not change. It will be still the linear combination of the same, of the new vectors. Okay, that is the property. So in general, if you have any vector x, y, okay, so how do you define x, y in the new coordinates? You need first how I can change, and you need how J can change. These are the only two things you require, right? How I changes and how J changes. How I changes, you need two numbers, right? How J changes, you need two numbers in 2D. So you just need 4 numbers. Is it clear up to this point? So in order to find the new location of any vector, you just need 4 numbers. If you need these 4 numbers, by the property of the linear combination, you can find any other vector in the space. Yes, clear up to this point? So suppose for any other vector in this space, I can write this as x times 1 -2 plus y times 3, 0, right? Is it clear? If I take any general vector in this space, in the new space, so this is any general vector in the new space, right? So this x, y will go to something called as x plus 3y and minus 2x plus 0y. This is my new location of this xy vector after the transformation, right? Is it clear? Any question up to this point? So just by looking at how the basis vector changes, I can find out the location of any vector in space. Okay. Any question up to this point? Is it clear? Yes, okay. So now let us do this. what does this imply? This implies that I can make the information that I require to transform anything is just like this, right? I pack it as a matrix form. So this is the transformation. This is what I require in order to, the 4 numbers that I require, I arrange them in a column and pack it as a matrix. So this is all I require in order to find out any vector in space after this transformation. So this is what represents a transformation. Okay, this represents how each vector in the space get transformed. Yes or no? And this is what simply represent is the 1, 3, minus 2, 0 is the product of this. If you solve this, you will get this, right? Is the matrix vector multiplication, right? So in general, what you want is, you just want how two vectors are changing, what are the new coordinates of 2 vectors, place them as a column of a matrix, and that is all you require. Okay, is it clear? So in general, if I say in general, if you have some vector which get changed as AB and say CD, something like that. Oh, maybe it's better to write AB, CD. So what this implies AC. What this implies is the how the first vector changes, right? The vector which you use as a linear combination. Okay, you can use any vector instead of ij. Suppose in your original you use u and v, suppose. Okay, so this column represents how u changes in your, what is the new location of u. Yes, and this is what is the new location of v. So you can use any vector like, and what will be the any vector w will be product of this times the original w, like the transform w is product of this with w. That will be the new location of w. Is it clear? This is very straightforward. So this is the concept of the matrix. Matrix represents the transformation. Okay. So and you define the matrix vector multiplication. Let us take an example. I think it will be clear very much after an example. So let me take a very simple example, which is by rotation by 90 degree. Okay, rotation by 90 degree. So what does rotation by 90 degree means? I have this space, I take this blackboard, I rotate it by 90 degree. Okay, so my initial, suppose I write I cap, which is 1 0, my j cap is 0 1, right? If I rotate it by 90 degree, so this means these are my 2 vectors, right? If I rotate by 90 degree, how does this will go? Now if I rotate it, it will be like this, right? Yes, if I take it, rotate it by 90 degree, it will be like this. So this is I is 1 0, j is 0 1. Now what are these vectors? This vector is, this is same as, so this is my now my I prime, and this is my j prime, right? This is my I and this is my j, right? So what is my I prime now? I prime becomes j, so it becomes 0 1, right? What is j prime? Minus I, so it becomes minus 1 0, right? So under this transformation, I, which is 1 0, goes to 0 1, and 0 1 goes to minus 1 0, right? Is it clear up to this point? So what is the representation of this? This matrix, this will be represented by 0 1 minus 1 0, right? Is it clear? Now take any vector. So if you multiply any vector by this matrix, that vector will be multiplied by 90 degree. Okay, you can take any arbitrary vector. So any arbitrary vector, suppose you take xy. So what will be the outcome? What will be the result? This will give you minus y and x. Yes? Is it clear? So this means any vector now get multiplied by or get rotated by 90 degree. And this is applied to any point in space. So all the point in space get multiplied by 90 degree. Okay. And from this you can also think of the concept of the inverse. If you calculate the inverse of this matrix, it will be the reverse rotation by 90 degree. Do you get me what I mean? If you take this matrix, take the inverse. So if you are rotating by 90 degree like this, if you apply the inverse of that matrix, it will again come back to the original. Yes or no? That is what inverse do. A inverse is 1. So whatever the effect this transformation has, you should undo that effect. Yes? Is it clear? So this transformation do rotation by 90 degree, the inverse should do the reverse transformation by 90 degree. That is all the inverse is. Okay, that is how we define the matrix inverse. Okay, physically. Now there is one more concept, which is the determinant of a matrix. What does it imply? Okay. No, not clear. Okay, so let us make it clear more physically. What physically determinant imply? Inverse you are clear, right? What inverse physically imply, right? Is the reverse of that transformation. That's all it is. Now let us take a very peculiar example. Suppose I take a matrix which is say 2 0 0 3. What does this matrix will do? So if I take any x, so let us do, if I take 1 0, this is my x, right? So what this do to the x-axis? What will be my new x-axis? What will be my new x-axis if I use this vector? This is my original vector. What will be my new x vector? Oh, I vector. This is I vector, right? So what will be I new? How you calculate I new? You multiply this 2 0 0 3 by 1 0, right? Can anyone solve it? What is the new vector? What is the new vector? Can anyone? What is the result of this multiplication? It's a very simple problem. What is 2 0? Okay, 2 0, and I can write 2 0 as 2 times 1 0, right? So what this transformation is doing to the x-axis is making it twice bigger, right? Now let us take the new, some other transformation. What is j new? So j new will be 2 0 0 3 and 0 1, right? What this will do? What is the result? 0 3. Okay. So it will be 3 times 0 1, right? Yes. So what this transformation is doing to j? It making j 3 times bigger. Okay. So in general, what this transformation will do? It will take any vector, make it x component to be twice bigger, make y component to be 3 times bigger. So if in general, if I take only a vector like this, so it will make it x to be twice bigger and y to be 3 times bigger. That is what this transformation is doing, right? Let us take, in order to build the transpose, let us take one more example, which is okay, this is for you to do the exercise. You should tell me the result. Okay, so I give you a matrix which is say 1 1 0 1. Now this is the exercise for all of you. Just give me the location of 1 0 and 0 1. What is the new? Everyone should solve this. So this is a matrix A. After you apply this on this and this, what should be the result? Solve. Who can solve first? It's a very simple 2 by 2 matrix multiply by a vector. It won't take more than 5 or 10 seconds. So what is the location of nu x? This is the example of shear. What is x? Nu x? Huh? 1 0. Okay. So x does not get changed. It's very okay. And what is y? Huh? What is y?
1.
What is y?
1
1 1. So what does this do? This transformation takes this one and does not change x, but it changes something y. So all the x component of the vectors will still remain the same, only the y component will change, right? That is what this transformation do, right? And from there we can define the determinant, okay? And it's a very how say, a very good way to define the determinant. For example, let us take all 3 examples, okay, that we did. The first one was the rotation by 90 degree. Okay, so rotation by 90 degree, it was, what is the matrix form of that? 0 minus 1 1 0, right? This was the first transformation. The second transformation that we did was 2 0 0 3. Okay, and the third transformation is just now we did it, the shear 1 0 1 1, right? These are the 3 transformations that we did right now. Now let us look at the area, how the area get transformed in all these three directions. Okay, so in this case the area does not change, right? Because you just rotating it by 90 degree. So the unit length, if I calculate the area, this one, like unit length in both, they still remain the same, right? Even if you rotate by 90 degree, right? In this case, how much the area will change? X getting 3 times, y getting 3 times, 2 times and 3 times. So how much will be the area get changed? It is xy, right?
6.
It will be 6 times the area, original area, right? In this case, how much will be the area change? How much will be the area change in this case? It will not change, it will be the same, because there is no change in y. It's only the change in the location, but there is no change in y, because initially it was here, now it becomes like little bit here, but still the y is still the same, right? Okay. Now this is how you define the determinant. For example, the determinant of this transformation is, what is the determinant of this? 1, right? What is the determinant of this? 6. What is the determinant of this? 1. So determinant tells you how much the area will change after you transform the space, because in first case and the third case there is no change in area, so the determinant still remain the same of this transformation, like it's still 1, right? But in the second, in this case, the determinant changes by the 6 times the original, because this transformation stretches the space, it scales the space, x 2 times and y 3 times, so that's why the determinant is 6. So usually this is the physical significance of the determinant, how much the area will change after the transformation. What is the unit area, whether it get rescaled or not, that is what you can get from the determinant. Okay, so in this case the unit area by change in the x region changes by 2, unit area in y region changes by 3, so the total change in 6, right? But this is a shear, simple shear. Shear means you are taking it just like that. Okay, it's like it from the square it becomes a parallelogram. Okay, so there is no change in area. Okay, is it clear? So determinant specify the area, specify what should be the unit area get changed after you transform your space. Okay, for a transformation the determinant is that. Is it clear? Any question up to this point?
So how do you define the unit area?
Unit area is just like the unit vectors, how you define it. Yeah. No, not I dot I. It should be the I and J, combination of I and J.
So the area is
I cross J, right? That is how you define the area.
yeah, I cross J. So you can prove that by saying that DOI is actually the transformation matrix I, and you
J.
compare I cross J prime.
Yeah, that is you can try. That is you can try. Means you can calculate the area by the original I and J, and after the transform I and J, and you can check it. And it's very simple. Like for example, in this case is very simple. Like your new I is like 2 times the old I, right? And in this case is J is 3 times the old J, right? From the transformation you can find out. So if whatever the area is given by this, it will automatically become 6 times.
But in the command center, I think when you transform coordinate,
Yes.
your error will not show.
No, why? Because if you scale it, if I stretch the space, because this is what this is doing. This is the scalars, right? It scales the x-axis by 2 and it scales the y-axis by 3 times. So if you scale, your area will change. Your unit space, or whatever the unit you are using for your measurement for the space, it getting 3 times bigger or 2 times bigger, so then it changes. The another thing is, because we are dealing with only the square matrices, but you can also use the non-square matrices, and those non-square matrices can represent the transformation of space. You can go from higher to lower dimension or lower to the higher dimension. Okay, you get me what I mean? Because let us take a simple example. Suppose I have a, say, A, B, C, D, E, F, this transformation. Okay, a simple, very simple transformation. I'll do this when I do the more mathematical concept, but this is only for the understanding, physical understanding. So if you have this matrix, okay, so now what you are doing, I told you what this column represents is a representation of I vector, and this is the representation of the J vector, right? So if you apply this, you say that okay, I am from the 2-dimensional space, now I am going to the 3-dimensional space, but in this 3-dimensional space I will be in a plane which is intersecting the origin. I cannot go beyond that, because that is what I am. What is this 2-dimensional space that I am right now is the projection of this 3-dimensional space when I project it to the origin. It will be a plane passing through the origin. It can be any plane, but should pass through the origin. Otherwise this transformation will not, means if you want to go from one space to another, that is how the transformation works. You can always go to a plane which passes through the origin, otherwise it will not work. Do you get me what I mean? Because when you are projecting it, the z component will always be 0. Do you get me what I mean? Otherwise this transformation will not work, because there is no z here. There is no z here, because in 3-dimensional space you have a z, but in this transformation there is no z, you only have 2. So what does this imply? The third component is always 0. So it means you are essentially in a plane which passes through the like origin where the z is like the plane passing through the origin, because then only you can project it. You cannot have something like here, because in that case that z will be non-zero. Okay, because in that place the third component, I am saying z, but it is the third component, third vector that you use to span that space. Okay. Yes.
You finished?
Yeah, almost. Yes. Yes.
So if this is three-dimensional, so the determinant should.
No, this determinant cannot be defined for.
No, for the three-dimensional.
Yes.
Determinant represent the larger volume of.
Yes, it's a volume.
Okay, so that means it should be I dot j cos k.
Yes, something like that.
To the transformation metric.
Yes.
And transformation means determinant represent the
Yes.
largest volume.
Yes, yes. So how if you go to the three-dimensional, it's how the volume gets scaled.
This is new for me.
Oh. If you go to higher dimensional, it is like the hyper volume that you say. So that is a common concept that you usually use for. So you can check whether if there is any scaling in your space by this transformation just by checking the determinant. Okay. So then you have, I think almost the concept is almost done. So from tomorrow I'll start with the mathematical definitions. I hope you will survive that. But today is just like the basic and the physical overview. So just to build up the subject, so that if I say something mathematically, you should know what I'm meaning physically. Okay, so that is all for today. And I think you all are familiar with the matrix. I assume that you are familiar with how to multiply two matrices, vector matrix multiplication, what is transpose, and so on, these basic operations. I assume that you are familiar with. If not, you can tell me, I can revise them tomorrow. Okay. So from tomorrow, I think we'll start with the vector spaces, the mathematical definitions, and so on. Okay. So hopefully you survive.
Thank you.
Okay. Yesterday what we are doing were the transformations. And if we take the transformation, we can have a matrix representation of the transformation. So in 2D, if we have some basis vector, say I cap and j cap. So what a transformation T implies, that what is the new representation of this I cap, and what is the new representation of j cap? You represent that as a matrix, right? So the first column is where I cap lands, and the second column is where j cap lands. That is a basic idea of a transformation, right? And for example, a simple rotation in 90 degree, how to represent a rotation by 90 degree, that we did last time. What is the rotation? By 90 degree. So where I cap is 1 0, this is 0 1, right? So when you rotate it by 90 degree, I cap will go like this, j cap will go like this, right? So I cap will land at 1 0, j cap will land at minus 1 0 1 and minus 1 0, right? So the matrix that represent this transformation is you take this first, place it as the first column. Okay, so it will be 0 1, and then you take this, place it as the minus 1 0. So this is the transformation that represents the rotation by 90 degree. Similarly, the other example we do it is very simple, which is the scaling. Suppose I take this 2 0 0 3. So what does this implies? This transformation implies, if you look at, because this is what it do to your first vector. due to what it does to the x-axis, right? So for x-axis, let's make x-axis twice the bigger size, right? And the y-axis it scales by 3. So now your y will be 3 times the original, right? Is it clear? And similarly you can do all other transformation. After that, what we find out that how a unit area in the system get transformed, and it is given by the determinant, right? So if I have this coordinate axis, suppose I have this unit area, right? 1 and 1. I take the measurement in any unit by 1, okay? So this is a unit area, right? But if I apply this transformation to this space, what will happen is my unit, this space will be stretched to this time, and this space will be stretched to, so now my unit area is this big, which is twice of the original and 3 times of the original. This is what this transformation do. Is it clear? And how you check it, how much the area get rescaled, you calculate the determinant of this transformation. So this transformation, after this transformation, if this is my unit area, if I rotate it, my unit area still becomes the same, right? There is no change in the unit area because I am just rotating it, okay? So in this case, when I rotate it by 90 degree, there is no change in area. So you can check it by the determinant of this. What is the determinant of this? D is how much? 1, okay. And determinant of this 6. So it means that it's rescaled by 6. So 1 unit area now becomes 6. Okay, a square of 1 by 1 becomes a rectangle of 2 by 3. Yes. So D is 6. So these are very basic cases, right? But suppose you get something called as, let me take it as a simple transformation which is 0 to 3 0. What does this transformation do? Or maybe make it not -3, maybe 3 0 is okay. So what does this transformation do? So let us first take the x-axis become y-axis, right? So my x-axis become y-axis. So initially it was x and y, now it becomes first x, oh this is my x. Now what is my y-axis? It becomes x-axis. Yes. So it just changed the axis, but it not only the change the axis, it also rescales it. So now 1 unit will become 2 unit, and 2 unit or 1 unit in y will become the 3 unit in x, right? Oh sorry, this is y. Is it clear? Now what is the determinant of this transformation? -6. You get a minus. What does it imply? I don't know. It's good. So what does this determine? This minus, so this transformation has a determinant of -6, right? Oh, -6. This has a 6. This has -6. What does this minus imply? So what is the difference between these two? The axis get flipped, right? So in this case the axis is on the right, y is on the like left side of the x, right? But in this case it's the opposite. So there is a change in the orientation of space. Your space get flipped. So it's like if you are on this side of the paper, now you are on this side of the paper. Yeah. Means now you are, if I view from this side or I flip the space, it's like that, right? If I draw it on the plane, you can imagine it from this side or the opposite side. So it's just the flipping of the space, that is what this minus sign gives you. Your space get flipped. You are viewing from this, now you are doing shifting the page, like If it is a plane, or if you assume that this 2-dimensional is a page, a paper, you are viewing the paper here and now you are flipping it. That is what this transformation do.
It's not
Okay.
like a reflection, right?
It's not like a reflection, it's like the change in the orientation. You are changing the orientation of a space, you are changing your axis. Now initially your axis goes like this, now your axis goes like this. So like going from this direction clockwise to anti-clockwise direction. Okay. So that is what this negative determinant tells you. Is it clear up to this point? What does this negative determinant tells you? Clear? Any question about the determinant, because this is very important concern what we are doing the next. Yes? What?
Just
Okay. Okay, let me go to the other. So let us take a special case again. Suppose I take 4-2 and 2-1. If I take this transformation, what is the determinant of this transformation? What is D? 0. What does this imply? What does this 0 imply? Can you think? No. Achha, where are the vectors are lying? Can you draw? Where are the vectors going? Where is x? So if I draw on the coordinate axis, suppose where is my new x? So it will be somewhere here, like 4 and 2, it will be somewhere here, right? And what is my y? It's somewhere here, right? So this is my new y, this is my new x, right? It's still on the same line. So the span decreases. Yes or no? Initially these two vectors can span the full 2-dimensional space, but now I am with this transformation, every point comes to a line. Okay, it's like I am taking the sheet of the paper and folding it into a line, right? Now I cannot go beyond the line, so there is no area because it's only a line. So your full space getting squeezed to a line, so there is no area. So this tells you that this transformation takes the full space and moves it into a line. Is it clear? The other extreme can happen is it can move everything to a point, to the origin. Okay. Now when it moves to a line, it means the span decreases. Now you cannot go beyond the line. After this transformation, everything goes beyond the line. Okay. So this is a special case when D is 0. How to think of this in the 3-dimensional? In the 3-dimension, if determinant is 0 means the volume goes to 0. So how the volume can goes to 0? So in 2D either you can go to a line or a point, right? Because both of them they have the 0 area. A line has 0 area, the point has 0 area, right? In 3D, if you have a 3D, determinant is 0 means either you can go to a plane, everything goes like 3-dimensional sheet, you project everything to this blackboard, which is a 2-dimensional surface, right? So this does not have any volume, or you can project everything to a line or everything to a point. So there are 3 possibilities, right? When the determinant is 0, either you can go to a plane or a line or a point. How to distinguish between these 3? Because determinant is equal to 0 does not tell you which object you go to. From your volume, either you go to plane, line or dot. So plane, line or point, all of them have determinant is equal to 0. So you cannot classify based on simply determinant. So in that case, what comes into picture is rank of a transformation. Have you heard of this term rank? Rank of a matrix or rank of a transformation? No? What is rank? Anyone knows what is rank of a matrix or rank of a transformation? It's a very basic concept. No.
A dimension of an image.
Yes. Can you explain them to maybe Penji? Can you explain it to Penji? So that she understands what rank is.
So you take a vector, transform it, and then you look at the dimension of the image of the vector space. So you take the whole R2 in this case. So you take the whole Rn, transform it by matrix M by N, and then you're looking at the dimension you get out of the transformation.
Do you understand?
You mean after transformation?
So basically what rank tells you is whether you go to a plane or a line or a point. That is what he is saying in some mathematical language. But basically if you have a transformation and if it has a transformation is full rank, suppose in 3D the transformation is full rank. So you go from 3D space to 3D space. Okay, that maps transform every vector to other space which is the 3-dimensional itself. It spans the full 3-dimensional space. Okay, but suppose this transformation maps this 3-dimensional space into a plane. Okay, so then the rank will be 2. Okay, if it maps to a line, the rank will be 1. If it maps to a point, the rank will be 0. Is this definition clear? Okay. So this is how you define a rank. So I'll make you more formal definition of the rank. But let us see what does determinant 0 means. Okay. So yes. Maximum rank should be the dimensionality of your space. That is what a transformation. It cannot take you from that to a higher dimension, right? Because you need additional information in order to go to the type. There are transformation which, like for example, I tell you, you can transform a 2D space to a 3D space, but it will be only a plane passing through the origin. You cannot go beyond that plane. Yes, but the rank still will be the 2. You cannot go beyond that. Okay, you can have suppose you can have a transformation, say A, B, C, D, E, F, right, which takes from 2D to 3D, right? But what happens is it takes the 2-dimensional to the 3-dimensional space, but this in the 3-dimensional space, the place where you lie will be a plane. You cannot go beyond this plane. So your rank still be 2. Okay. So let us move to let us again go to this case where you have the determinant -6. Okay. So what this will be doing? Think of this transformation. Okay, when you have the negative determinant, what is happening? Suppose I start from this case and I move to this case, right? That is what is happening, right? I start with this orientation, means this configuration, and I move to this after the transformation, right? So my axis got flipped. Okay. Now let us make us a very simple case where I have this 1 and 1. So there is no scaling. Okay. So what is happening is, take this as a very like if you study this piece by piece, these will be getting close and close, and after some time they will get exchanged, right? Do you get me what I mean? If you study this, think of this as a movie playing. So how this will work? It will be like this. So determinant will, like the area will become closer and closer. At one time it will be 0, then again it will go back to normal, right? Do you think of it? So, the time when it crosses, you need a notation to represent that the axis got flipped. That is why it comes the negative, that it represents that your area is increasing, but still you have a change in the orientation of the space. Okay. Do you get it what I mean by a negative sign? So, it represents when you change your axis. Like for 3-dimensional with the right hand rule, you can represent the 3 axes, right, I, j and k, right. But if you cannot longer represent it by I, j, k, it means it get flipped. Okay. So, that is when you will get the negative determinant. So, any change in orientation of this space will give you a negative determinant, and the magnitude of this determinant will give you the scaling of the area or the volume or hypervolume. It depends on which dimension you are. Okay. Is it clear? So, so let us move to a very, so you know how to calculate the determinant, right? AD minus BC in 3 dimension, you know how to do it, 3 by 3 matrix and so on. I will not go into the details how to calculate the determinant or the inverse. I assume that you know that. If not, I can show you on the board, but it's okay. Okay. So, so why all these things are useful? Like whatever we have done up to so far, we only build the basic, we study some physical like geometric representation or the geometric meaning of all these terms that we do in the linear algebra, right. So, why these are important? Okay. So, let us first take a very simple example which we always encounter in any branch of sciences. You have some variables, say Ax, yes, okay, I will do that.
Can you use other colors? It's hard to see.
Yes, I can follow all the requests. Let us do only the 2 dimension, say which may be alpha Cx plus dy, maybe gamma, is it the notation? Okay. So, suppose you have 2 variables and there are certain equations which relate them, and I assume that these 2 equations, they are the linear, there is no fancy function such as sine, cos, log, whatever, which are nonlinear function, there is no product term involved or higher power term involved. So, this is a very simple system which is the linear system, right. One of the beauty of this system is you can represent them as a product of a matrix and a vector, right. So, you can represent this like this is what we have done before when you use the transformation, right. So, you can represent this as a, b, c, d, x, y and some alpha and gamma, right. This is a very simple way to represent it. Now, what is happening here? So, if you think of this as a transformation, it is this transformation taking this vector and mapping it to some other vector, right. That is what this is doing. If you think of a linear transformation, so this is how it is working, and you can simply represent this as Ax vector is equal to V vector, right, something like that. It is a very simple notation of this. So, the solution will depend how the x, how the A changes the x, right. If it maps to a normal space, 2D space, then you can find a unique solution, right, because you see that a 2D space can be mapped to a line, right. So, if this A take this vector maps to another vector, right, if this A does not do any like shrinking or the squeezing of the space, it does not take, means it takes this transformation has a rank 2, suppose what I mean by the rank in this case. So, if the transformation, after the transformation your space is still 2D space, then it will have a unique solution. Why it will have a unique solution? Because you know, like from the basic, that every point has a vector notation, right, and you cannot have more than one point representing like more than one vector, right? One point cannot go to two vectors, right? So, if a vector it get transformed, it will be transformed to a unique vector. Yes? A vector will get transformed to a unique vector, because that is the property of the space. All the lines should remain line, right? The parallel line should remain parallel. That is what the linear transformation do. Yes? So, how to mathematically prove it? So, we are going to do that, and a way to think of it, like to think of this transformation is in terms of the applying a similar transformation which has the reverse effect, which we call as the inverse. Last time we discussed this, right? You can have a transformation and play it in reverse. So, if you rotate it by 90 degree, you can have another transformation which can rotate backward in the 90 degree, right? So, that is the inverse of this transformation. But what is the guarantee that the inverse exists? Can you find the inverse? Okay. So, you can think of this from this point. Okay. If I map everything to the point, to a line, can I go back to the normal space? I cannot go, right? If I project everything to this, like 3D to this plane, there is no way I know which point is where, right? After I map, all the information is lost. My 3-dimensional information now it is represented in only 2 dimension, right? So, I cannot take back this information. So, I cannot get the inverse, right? I cannot construct a backward transformation which generate the full 3D space from the 2D space. Okay. So, like for example, a simple is like 90 degree rotation, you do the clockwise, then the opposite will be the 90 degree anti-clockwise rotation. Clear? So, let us do how to construct this inverse of a matrix. Okay. So, in the simple sense, suppose I take this 90 degree rotation. So, suppose this A is 90 degree rotation. So, what I do is I apply on both sides the 90 degree anti-clockwise rotation which I define by A inverse, suppose. Okay. So, I do A inverse A, right. So, this will give you the no transformation which is given by the identity, right. And so, x, now in your case x will be given by A inverse V, right. What is A inverse? A inverse is a transformation, right. So, how to solve this equation is simply like because you do not know x and y, right, you do not know x and y, but you know this vector V. So, what you do is you take this vector V and think where it goes back. Yes, you can think of this as where it lands back to the x and y, and that will be your solution, because you know that there is only, if there are no like abnormality, there is only one point where this vector will land, right. So, that is what we are doing here. We are, it's like, so what this equation tells you, this transformation takes x, take it to some vector y, right. Now, we want to play it backwards. We say that okay, we see where this vector V comes from, and that is what A inverse do. A inverse plays the movie in the backward direction. Okay. So, vector S get moved to vector V, that is your original case. Now, you know the vector V, now you play the movie backward. So, vector V will get transformed to vector x, and you will get the vector x. That is all we are doing here. Okay. So, that is how you solve this equation. Okay. So, let us first use the case when D is not equal to 0. Okay. So, there are different scenarios. So, suppose for this transformation, any transformation A, D is not equal to 0, means determinant is not equal to 0. Okay. Oh, not equal to 0. You should correct me if I write something wrong. I am very sleepy. Okay. So, in this transformation, what will happen is you start from a 2D space and you go to a 2D space, right. Determinant is non-zero means You start from the same, you start from some space and you end up with the same dimensionality of the space, right? Yes? Yes. So in this case determinant is non-zero. So in this case a unique means you can find an inverse so that you can map it back to the original vector, and it's very very easy to do it, right? You know how to calculate inverse of a like factor, and you can do it, and you can simply test it out by the like the 90-degree rotation. That is really your homework. Calculate 90-degree rotation. You know what the matrix representation of 90-degree rotation is. Okay, calculate the inverse of it and try to multiply both. That will give you identity. That is a very simple thing you can do, or the scaling you can take the inverse, multiply both scaling and the. So in some sense, like if it is the scaling 2 by 3, what will be the inverse? What will be the inverse of this? Can you assume? 1/3, right? So it will be 1 by 2 and 1 by 3, 0, 0. You don't even have to calculate it. Just by intuition you can calculate what should be the inverse. Yes or no? Oh, not 6, it's 0. Okay. So just by intuition you can do many things without even calculating it. Okay. So now let us go to the point where you have d equal to 0. Okay. So if you have d equal to 0, does the solution exist? Yes or no? No. Thiti can answer it. If the determinant is 0,
Yes.
do the solution exist?
Well, accept 0, yes.
Huh? If determinant is 0, can you find the solution?
Not for general vector.
Not for general vector, but what cases?
So accept 0.
Except 0.
But then we cannot get to the original anyway.
You cannot get to the original, but can you find a solution to the system of equations? That is what I mean.
No.
Huh?
Not in general. So I mean, it would be no. It's only for vector 0.
No, not only for vector 0. The case is
Yeah. So
if you are mapping means if you are mapping it to this axis, like all the space get mapped to this. If vector v lies on this vector, then you can find a solution. Do you get me what I mean? If vector v lie on this line, then you can find a solution. Otherwise, there is no solution. Okay. So this vector alpha gamma should lie on this line in order to get a solution. Then only you can, because what is happening? The space is getting mapped to this vector, right? If the original vector is from this, you can always find a solution. Like there will be many solutions possible, because many points getting mapped to the same line. Is it clear? Why you have the many solutions? Because all the points in space getting mapped to the same line, same vector. So there are infinitely possible solutions. If your vector v is in this, if vector v is somewhere here, because all the space getting mapped to means all xy goes here, right? And your vector v is here, there is no possible way you can have a solution. So in that case there is no solution. Okay. The only thing is when vector v is here on this line and all the xy are mapped on this line, so there are infinitely many solutions. Is it clear why you have different sort of solutions? If d not equal to 0, you have the unique solution, right? Because every point get mapped to a vector. Yes, every point get mapped to a vector. So there is a one-to-one correspondence. So you get a unique solution. But if the transformation has d equal to 0 and your final vector lie on the line, you have infinitely many solutions. If the final vector does not lie on this line, you have no solution. And that is true even for 2D, 3D or whatever dimension you are. In 3 dimension, same thing you can think of is if your vector lie on a plane, you can have infinitely many solutions. If lie on a line, you can have infinitely many solutions. There are the two possibilities in that case, right? Because a 3 dimension can be mapped to first a plane. When it is mapped to a plane, then there are many lines of solutions. Okay, because many lines can be mapped on this plane, right? If you have a line d equal to 0 and everything mapped to a line, then you have a planes of solution, because many planes can map to a line.
You mean this transformation is do something like a constraint?
You know, this transformation is not doing anything. Transformation is just mapping the space to a line. For a 2D, what this transformation is doing is taking the full space and mapping it to a line.
Yes.
Like, okay.
It's like a constraint in the
Constraint, yes, it's like a constraint. So you have this line. Now your vector, if it lies on the on this line, so if it lies on this line, then you can map many vectors on this line, right? On this vector. So there will be many vectors can go to this vector. So you have infinitely many solutions. Okay, but suppose this vector is outside this line, then you don't have any solution.
How do you find the line?
Oh, that line is from this transformation, from this matrix. Because matrix, suppose the matrix is maybe 4 2 2 1.
Okay,
So this, the full space will be mapped to this line, right? Which is like the first, because your x vector is this, or maybe I draw with blue. So this is your I hat vector, right, where it lands after the transformation, and this is your j hat vector. Okay. Now suppose your v is say 0 3. Okay, for this matrix your v is 0 3. So 0 3 will be here, right? So your v vector is here. This is your v vector, right? It is outside the line, so you cannot find any solution, because your I is here, j is here. You cannot go there by any combination of these I and j. So there is no solution possible. But suppose I say that your v vector is something called as 8 and 4. Okay, if your v vector is 8 and 4, so it will be somewhere here, right? This is your v vector. So many point in space, like if you take this point, because it get mapped to here, you take this point, it get mapped to here. So you can find many points which satisfies this relation, because all the points get mapped to this v vector. Yes. So you will find infinitely many solutions. So this is the all. In 3D, what will happen is you have a 3-dimensional space. So first it get mapped to a like suppose it's like that you project everything like this. Okay. So you will have a family of solutions which are the lines, like all the lines get mapped to this plane, right? So the vector, if it lies on that line, there that many will be the solutions. If you project everything to a line, then there will be the planes which get mapped to the line. Yes or no? How you map a 3D to a line? Every plane will have a mapping to a point, right? Then only you map the 3D to a line. Every plane get mapped to a line. Is point.
It's because there are some vectors get mapped to zeros vector, right?
Not some vectors get, means there will be many vectors which get mapped to the 0 vector.
Yeah. So it's because of that
Yes.
you get infinitely many solutions.
No, not because of that, but because of that, because yes, like because this vector will be, this point will be this, like this is your point where the solution exists. It's like 8 4, right? Somewhere here. So there will be many, like if the space gets squeezed like this, so all the solution which all lie in this line will get squeezed to that point.
Yes. I mean like, so if you map x to v, then and you have vector that get mapped to 0, then you can always say that the x plus that vector is also a solution.
X plus that, you can say that also. You can, because you can take the linear combination of the solution. That is also that is also true. But the point why I'm not saying about that point. but what I am saying is because there will be many, by itself there will be many solutions. That is also a possibility, but by itself there will be many solutions which get mapped to the same point. So everything on this line get squeezed to this point, and there are infinitely many points on this line. So all these are the possible solutions. Okay.
Suppose you have three-dimensional
Yes.
transformation matrix.
Yes.
So these three-dimensional transformation matrix represent three vectors.
Yes.
Three positional vectors.
Yes.
So that will give you a line, but in 3D.
Yes. It will give you a line of 3D.
Mapping transform a volumic space of coordinate into
The line. Yes. So how you map a 3D space to a line? All the plane. So the 3D space, if you consider to be made of the plane, all the plane go to a line, go to a point.
yeah. So that when you said to me that you consider a rank so that you will know. So this zero determinant can come to a plane, a line, or a point.
Yes.
So how to use the rank to?
Yeah. So that I'm going to show you. But what I mean is, so suppose for a 3D, if the transformation has, I'll define the rank, but if the transformation has rank equal to 3, okay. Suppose the transformation, because the 3 by 3 matrix, right? If it has rank 3, it means it has 3 linearly independent columns. You cannot represent the other 2 columns, like for example, in this case, the rank is 1, although it's a 2 by 2 matrix, because you can represent one column in terms of the other. Yes or no? These 2 columns are not independent. Yes or no? So in this case, how many linearly independent columns you have?
So you have to check this independency first.
Yes, you have to check that is what gives you the rank. So in this case, although it's a 2 by 2 matrix, it has 2 columns, but one column you can represent in terms of the other. So it has rank 1. So that's why everything get mapped to. But in 3D, suppose in 3D you have 3 columns, say maybe column 1, column 2, column 3. Okay. So in these 3 columns, if you can represent one column in terms of the other 2,
Right.
so it will have rank 2, right? Because there are only 2 independent columns. So in this case, you will go to a plane. Okay, I can give you an example. Say maybe.
I thought I understand at the beginning, but and then I think I got lost again.
So suppose you have the 3-dimensional transformation, right? Now in this case, you can assume that this column is the sum of these 2 columns, right?
Which one?
The third column is the sum of first 2 columns, right?
Okay.
Right. Means maybe make it my 1 something like this, and it will be 2. Then it will be more clear. Okay. Otherwise, it will reduce furthermore if I introduce 0. Okay. So now the column 1, column 2, and column 3, right? Column 3 can be represented as the linear combination of first 2 columns, right?
Rank 2, right?
This is rank 2. So what this means? It is rank 2 means it takes the 3-dimensional space and makes it into a plane. Okay. But suppose I do something like 1, 2, 3, 2, 4, 6, and 3, 6, 9. Now this column is the twice of the first column, this column is 3 times the first column. So it has rank 1, because you need only one column to represent all 3 columns, right? So it has rank 1. So what this will tell you? This will tell you that you will have a line only.
Okay. So rank 1 is a line. So
Yes.
So what rank is the point?
Rank 0.
Rank 0.
Everything 0.
Everything 0.
Everything mapped to the 0 space.
So
Means everything mapped to the origin.
so rank 2 is a plane.
Yes. Rank 3 is a volume.
So you make me difficult to put the lecture notes, so I don't know how to write this.
Okay. I can provide the lecture notes, but you should give me.
During my lunch break.
Huh.
Alright.
What is the time? Is it?
Useful, very useful.
Yeah, means this is. I'll formally introduce maybe in the next lecture. I'll do the mathematical. But what I want to do is build the subject. so that when they go to the subject, because you can find the definition and everything in the any place in the books or every place, but I want to make them understand the physical meaning, because when you look at the book you will find the mathematical definition and it's not, you will not understand what it means like physically.
Yeah,
Yes.
yeah, this is very digestive. It's like a biscuit. And you are the Pradeep who lead the way with your Pradeep light.
So, this is what this is how I learned it, so I'm just giving the knowledge that
Sometimes it's dark for me.
it's okay, we can discuss anytime. So, this is what I define by the rank. So, the rank is defined by the number of independent columns in the transformation you have. Okay. Oh, sorry. So let me formally.
Want to say that the rank is the maximal number of basis vector in the image space.
Yes, in the image space, yes. That is the mathematical definition. So, that is I am going to define. So, suppose you have any transformation. So, what does the column represents? The column represents the transformation of the basis, how the basis get transformed in the new space, right. So, in the new space how many bases you have, independent bases you have, that is the rank of the matrix. Okay. Is it clear, this definition what Thiti, so maybe I will define.
It's even worse, right? Sorry.
I will give you a very basic definition, like very layman definition. You will think that this is a joke. Number of, or maybe number of dimensions in the output of the transformation, in the output space of the transformation, right. You can think. This is a very basic. So, you make a transformation and find out what will be the dimension of this output space. Okay. After the transformation, what is the dimension of the space? That is the rank. And this is equal to the number of the independent bases in that space. That is what Thiti told. You can directly relate it. Okay. Number of dimensions in the output space of the transformation, right? Yes. In the after you transform the space, what will be the okay. So, like for example, 3 by 3 matrix, rank 3 means the output space has the 3 dimension. Okay, let me, my board work is very bad, so please forgive me for that. So, if you have a transformation which is given by the 3 by 3 matrix, so for this transformation rank 3 means your transformed space has 3 dimension, 3 independent basis vector, right. Okay. If it is rank 2 means it is a plane, right, means 2 independent basis vector, right. If it is a rank 1 means transformation takes the 3 dimensional space to a line, it squeezes everything to a line. So, it means you have only 1 dimensional basis vector, and rank 0 is a very special case, everything to a point, everything it's like brick crunch in cosmology.
If the 2 columns add into the 3rd column, so this is rank 2.
Rank 2, yes. Like in this case, it is rank 1.
Okay.
I hope I am little bit mathematical now.
So rank 0 is in all the elements component are 0.
No, yeah, all the elements are 0, but basically what it means that you are taking the full space and shrinking it to the origin. That is what it means, which all the vectors are get mapped to the 0 vector.
I like that because it's
You have a question?
Any question?
Yeah, that's
Yes.
why so normally we have maximum rank 3.
Not maximum rank 3. You can have a transformation as 4 by 4. It depends on which space you are acting on. In linear algebra, you can have n dimensions, maybe 1,000, 10,000, even infinite dimensions you can work with.
But it doesn't make sense if you have like a rank 6,
Yes,
you give the picture.
it's very hard to visualize it. But okay, in linear algebra, what this dimension means, like for example, let us take the example of computer scientist. Okay, computer scientist, suppose he want to study this university, so he has different features or different parameters, like he can study this number of funds, number of papers, number of students, number of teachers, number of buildings, number of xyz. So each of these represents one dimension. Do you get me what I mean? And when you, but you can also say that whether these dimensions are independent or not. Okay, that will give you by the rank. If there is a, like if some dimensions are dependent on the other, you can decrease it. That will give by the ranks. Do you get me what I mean?
This means in another sense, if we have the in the computer science as perspective, we have the image in the real image, like
Yeah.
the image of the dog.
Yes.
And if we have transformed to the another resolution,
Yes.
I mean the
Another image, yes, smaller image.
resolution.
Yes, ma'am. Yes.
That's mean like that.
Yeah, that is, you can do only that
Like
in the multiple ways. One is you can also do the PCA or like SVD and so on.
Like
But without loss of information, if you want to do it, you use
the transformation.
transformation. Means if there exists a transformation which can easily represent it into a lower dimension, it means that this transformation has a lower rank.
Yes.
That is what it basically means. It takes a 3-dimensional space to a lower dimensional space and so on. Yes. So this is what we call as the column space. We also define another mathematical definition. So column space is basically the number of dimension yes, is the span of the columns of the matrix. Like column space is, if I have this matrix, like I have this matrix, it has only one dimension, right? So I can go only up to the line. So means I can generate all the points in this line using this matrix, because all the space get mapped to the line. So in each point on this line I can find a vector which can be mapped to this line, right? Yes or no? So that is what defined by the column space. Column space is what are the vectors that I can get to from this transformation.
Column space is an object before the transformation.
No, column space, like I have a transformation. So what are the vectors that I can get from this transformation? That is the column space.
What are the vector I can get?
What are the bases?
Not the bases. Bases are different. Bases are the, like you can choose any basis, right? Bases are the number of independent dimensions that you have, right? Or number of independent vectors that you have. But column space is the set of all the vectors that this transformation can take you. Like for example, if I have Ax is equal to V, if this is possible, like all the set of V's will be your column space, if I am not wrong.
Yeah, don't mix the dimension with the space you add, because like for example, if you want to explain the gas of two molecules, for example, you could represent it two ways. You could say the particle 1 have velocity v and another particle 2 have velocity v2, or you could say that, or I write the velocity of two gases molecule in 6-dimensional vector, and that vector of 6-dimensional define the state of the gas. So the state of the gas is 6-dimensional because you need six numbers to fix the behavior. And now if you say you you're not looking at only velocity. If you're looking at the position, then it will need 12 numbers because it will need like three-dimensional vector, three-dimensional position vector for the first gas, and then three-dimensional vector for the vector of the first gas molecule, and then the second gas molecule for three vectors for three components for the position and another three components for the velocity. So that would be a configuration space of the two molecules.
Yes, molecule.
12 components.
Yes.
So that would be 2n.
So the first thing is, it's not a dimension, it's a space. It's a space. Okay. It's not a dimension. It's like rank is a dimension. Space means it has the set of vectors.
Yeah. So column space means the space that contains all the vectors that this transformation can take to.
Yes, means after the transformation, what are the vectors that you can possibly get? That is a basic, very basic definition of the column space. So if you apply the transformation to the space, what are the vectors that you can get? That is the column space. Okay. Not too mathematical, but I hope you understand it. No.
You want to write the mathematical first and yeah.
Okay, so there is one more thing. Suppose in this space you can take a vector and take it to the zero vector. That is also possibility, right? You can take any vector, like for example, the example that I gave you, like suppose you have this space and everything goes to this line. So you project it like this. So there is a set of many points which can go to this zero vector, right? So all the points in this line will be moved to zero vector, right? Because you are squeezing the space like that. Is it clear? So you have this space. Okay, you have this space, and what this space do is like you have this blackboard, and what this space do is it shrinks the blackboard into a line. So it takes everything like this. So the output will be you get this line, right, which is from the origin. Forget me. Okay. This is the result after the transformation. So initially you have this two-dimensional space. After the transformation, everything moves to this line. Now when you move to this line, there are like in the original space there is this line which get mapped to this zero point, right? Because if you squeeze it like this, all the points here will be mapped to zero. So what this is, this point will map to here, this point will map to here, like something like so. All the points will be mapped to zero, right? So there are many vectors which get mapped to the zero. Yes, and this is what you define as the nulls or the nulls, or the kernel. Null space, the null space. So this is the column space, then you define the null space. Null space simply defined at all the vectors which can go to the zero. Okay, and this is another name which is the kernel. Okay. And Thiti told me to explain to you the rank nullity theorem. Okay, so rank nullity theorem simply tells you that the dimension of your space will be sum of the two, the rank of the vector and the null space that it moves to. It's very straightforward. If you think of it, it's a very straightforward answer, right? Okay. Let me write it down in a very formal way, not a mathematical way, but suppose there is a transformation T which takes this space V to W. Okay, is it clear? So it may be a three-dimensional space, it goes to a two-dimensional space. It may be a three-dimensional space, go to one-dimensional space, or any n-dimensional space, go to m-dimensional space. Whatever this transformation do, it takes one space and it goes to the another space, right? It can be a lower dimension space or the same dimension space. Okay, so what this rank nullity theorems tell you that the rank of this transformation, which is, what is the rank of this transformation? The dimension of this space after you get it, that, yeah. So this is rank T means the dimensionality that you get after applying this transformation, right? Plus the null space of T, okay, will give you the dimension of V. Is it clear? It is straightforward, right? This is very straightforward. So I don't have to prove them. They understand it without proving. Is it clear? It's very straightforward, right? Because this dimension of V, some of this dimension goes to 0 and some stays still with the rank. Like if it is a 3-dimensional object, so suppose the rank is 2, so one dimension goes to 0, right?
That means if we have a dimension V minus dimension of the U, it will be the
nullity.
No.
Yes.
If the rank of T is the dimension of the V.
W, yes.
Oh, okay.
Is it clear? So I think I'll stop here. So let us, oh, you are calling him? Oh. So now we will going to do the change of basis, and what change of basis simply means the coordinate transformation. You are in one coordinate system, you go to the another coordinate system, and how you transform them both, and how to make sense of this kind of transformations. Okay. So suppose so let us go to the basic definition of vector. If I say a vector 2 maybe 3 2, what does this vector tells you? What is this vector? What these numbers tells you? This number tells you how the basis get transformed, right? It is a recipe how to start from the origin and reach the tip of the vector, right? That is what this. So for this you assume a coordinate system. You have like the axis, maybe I write it as x and y. So what these numbers tells you? These are the coordinates for this vector, right? So what this tells you? This tells you how the unit vector in s direction gets rescaled. Like how many steps you have to take in x direction and how many steps you have to take in y direction in order to reach from the tip, from the origin to the tip of this vector. So in simple sense you have to take 2 steps, 2 steps in the, or 3 steps in the x direction and 2 steps in the y direction, right? So the point where you reach will be the this vector which is given by this vector, right? So it just tells you how the axis get it rescaled in order to reach this vector, right? In physics or in linear algebra, these numbers they represent the coordinates of the point, right? Yes or no? They represent the coordinate from the origin to the tip of the vector, right? In physics it may be a very different meaning, because in physics the vectors are not rooted at the origin. In physics you can have like you can take this vector to any place in space. So in that case that is not the coordinates. Okay, you get me what I mean? So the coordinates are only in the linear algebra when the vectors are rooted at the origin. Then only you can say that these 2 numbers are the coordinate of this point. So this point is 3 2. Okay, the point and the vectors are different. This is the coordinate and this is a vector. Okay, so coordinate you write something like this, vector you write something like that. Fundamentally they are different, but because the vectors are rooted from the origin, so they coincide with each other. Okay, but if you have any vector somewhere in the space, the coordinates and the vectors will be coordinates and the vector elements will be different, totally different. Okay, clear? This point is clear, right? So now let us assume that we have a vector which is in the V vector, and we are using the I and j basis for this, and suppose there is some alien, okay, and he represents this same vector in some other coordinates, in some other basis vectors. So, suppose he use another basis vector, say B1 and B2, which is different from this, right? Yes or no? And for them it is the same vector, so it will, right, but for him the coordinates are different. For us the coordinates are 3, 2, for him the coordinates will be A, B, or whatever you maybe say A and B are the coordinates for this, okay, because they use a different system to measure it, okay. So, according to this coordinate system for the alien, the vector V will be A times B1 plus B times, or maybe alpha and beta is the better representation, I think, right. Is this vector represented in this coordinate system or in this basis? Okay. They use a different axis to represent it. I use I and j. So, in this case this vector will be, suppose I have the, say what I use, maybe A B is better to use here. So, A I cap plus B j cap, this is the V vector in my representation, right. It is the same vector, but represented in two different representation. One is represented by the person who belongs to the earth, the one who is some alien, suppose he uses a very different coordinate system. Is it clear? Now, how they both are speaking the same thing, but in a very different language, right. They are speaking the same thing, but in a very different language, because their bases are very different. So, how to make sense of this? How to convert one into the other, or like change, how to come into a common ground, how can you understand what he is saying? Because if he give you this number, you will not make any sense, right. If he just give you that these are the coordinates for my vector. So, for you it will be alpha I cap plus beta j cap, right. If he just give you the coordinates, so this is what you will represent it, right, which is not the same as this one. So, you will get a very wrong vector. This vector is not same what he thinks of the vector, right. So, you should have a way in order to find what exactly what he means by this vector when he give the coordinates, okay. So, let us take an example, I think is better. Suppose you have a vector 3, 2, and in this coordinate system, suppose it is represented by, in his own coordinate system, 5 by 3 and 1 by 3, okay. So, this is the vector in his by 3 and 1 by 3. This is the vector in B basis, okay. In I j basis you have 3, 2 representation, in B basis is 5 by 3 and 1 by 3 representation, okay. So, this vector is 5 by 3 of B1 plus 1 by 3 of B2, right. But he will treat this B1 and B2 as same as 0 1 and 1 0. Yes or no? Do you get me what I mean to say? For you, what is I cap? For you, the I cap is 1 0, right, and j cap is 0 1, right. For him, the B1 for him, not according to you, for him B1 is 1 0 and B2 is 0 1. In the local reference, he will treat B1 as 0 1 and B2 as 1 0, okay. But for you, this B1 will not be 0 1, for you this B1 will be something else, right. Is it clear up to this point, the setup? Yes, any question up to this point? This is the setup. Now, we will try to figure out how to use this information in order to transform the vectors, and how to use the transform. And so let us suppose that, okay, so what I will do is I will take my coordinate system and I will see what B1 looks like in my coordinate system. That I can do, right? And the origin should match, that is the property. The 0 vector should always be the 0 vector for every coordinate system, right. So, the origin should match, but so it will look like something like this. So, this is your coordinate axis and this is what his this is what his coordinate axis will look like. The green is the alien reference like alien basis and the white one is your basis, okay. And there is a vector inside this, maybe orange color vector, which is this V vector, okay. It is the same vector, but according to him this will be like, the coordinates will be like this, which is alpha, or which will be like 5 by 3 and 1 by 3, and but for you it will be like this, what is 3 2, 3 and 2. Is it clear? This construction, this is the construction. But one thing you can do is, you can in your coordinate system you can always find B1, right? Can you do that? You see what B1 looks like in your coordinate system. Yeah, okay. So, B1, suppose in your coordinate system B1 is minus 1 1 and B2 is B1 is 2 1 and B2 is minus 1 1. This you can find out just by looking where his axes are, right. And just by using this information you can find out what he mean by V in his coordinate system, okay. So, we will try to figure out what we mean by this, okay. So, suppose you want to change your coordinate system to the new coordinate system, what will you do? How you can change it? You can just simply apply a transformation. You can transform, if I rotate my coordinate system from here till here and scale it accordingly. So, I will reach in his coordinate system, right? Yes or no? So, how I will do it? How I can do it?
Can you write one basis in another basis?
Yes, but I told you before, they know it. How I do it? You know, this is the new location of your basis, right?
Is B1 need to be a unit vector?
No, not necessarily.
And then how do you write down B1 is a 2 1? You want to compare the unit vector.
So, I am measuring B1 in my I treat B1 as a vector in my coordinate system.
It's a unit vector
It may not be a unit vector.
in your coordinate.
In his coordinate, in his scale, it may be a unit vector, but not in my.
Okay, so hang on. You with me or you with him?
I am with you.
Okay, good. So in our coordinate system, so that doesn't look like unit vector, but then in his
Coordinate system, it may be a unit. He may treat it as a unit vector, because he may have a different unit of scale, unit of length. Yes,
together, right?
yes, yes.
Otherwise confused.
Okay. So, do you remember, do you understand what I mean to say? This B1 for you is not a unit vector, but B1 for him is a unit vector, because he treat B1 as 1 0, just like you treat I cap. You treat I cap as 1 0, right? So, he treat B1 as I cap, okay, because, okay. Let me explain it by this way.
In the usual norm, when you write, the full formulation should include the norm of the basis. But usually we pick the basis to be normal and orthogonal.
Yes.
So the norm of the basis is equal to 1. But if we return to the full generality, then the norm of the basis should still be in the norm formula.
So, what I mean by this is, in a very basic sense, I construct my own coordinate system, right? I construct my I and j. I can construct it any way I like. There is no there is not unique. The The only thing is I should span the full space. I can construct any two vectors, it may be orthogonal, it may not be orthogonal, that spans the full space, that will be my basis, that will work in linear algebra. The only thing is that linear combinations should, I can go to the full space by with these two vectors. So, I can choose a basis like this to start with, or I can choose a basis like this to start with, or I can choose a basis like this to start with, I can choose any. This is my construction, this is how I define my system, that is not unique. So, you can construct your own system, I can construct my own system, Burin can construct his own system, and the problem lies is when we talk to each other, right, because if I tell the location of a point in my coordinate system, it will be different in your coordinate system, it will be different in Burin coordinate system. Like the only thing that matches is the origin is the same, we agree that the 0 is the same point, okay, that is the only thing that we agree, but the axis can be rotated or scaled. Suppose I use maybe a meter as the unit of length, Burin can use as a kilometer, Donut can use as a centimeter, right. So, the scales are also different, so that we can do all. Yes, for all of us, if I say 2 3 in my coordinate system, it may not be 2 3 in your coordinate system, it may be some other point in your coordinate system. So, this is the problem which usually we arrive when we deal with any system. If I represent system in my own language, you should be able to understand it in your own language, in your system, in your like coordinate axis, that is what we are trying to do. So, there are two individuals, one defined a point in space or a vector by some xy or ij coordinate system, right. There is another individual who defined his own coordinate system in terms of b1 and b2. Now the problem arises, this another individual, he said that my point is 5 3, like this is my point, this person says this 3 2, okay, and both are different, right. If they say that the points are same, then it is understandable that they are talking in the same language, but for them the same thing, the same measurement is different, right. So, it means they have a different coordinate system. So, how to convert between them? How can this individual can make sense when this says 3 2? Okay, so if I say my vector is 3 2, you should be able to understand what I mean by 3 2, not in your own language, but also in my language. Like just like I mentioned, like for him this is the vector, right, but for you this is the vector, like for you it will be like 5 by 3 I cap plus 1 by 3 j cap. If you say 5 3, this is what you mean, but this is what he mean, but this is what you understand, both are different. Yes, he says only 5 3, but this is what he meant by 5 3, because his coordinates are b1 and b2 and he represents 5 3 by this, okay. But because you are using a different coordinate system, this is what you understand. So, you are understanding something which he is not saying, he is saying something and you are like capturing something else. So, we want to remove this problem, okay. So, this is what we are trying to do. Is it clear, the problem here, right? So, how to do it? So, yes.
If the original point
Huh?
is the same, we cannot do this.
No, like whatever point, I am saying that it's the same point, but he can say that this point is 5, say 5 10, he can say this point is 5 10. So, for you is different from what he says 5 10. For him the 5 10 point is 5 b1 plus 10 b2, right. For you 5 10 is 5 I plus 10 j, and I and b1 are not same. This is what you understand and this is what he said, that is the problem. Similarly, for you, you say 3 2 point, for you this point 3 2 means 3 I cap plus 2 j cap, right. But if you say that 3 2, he will understand it as 3 b1 plus 2 b2. So, you are saying 3 I cap plus 2 j cap, but he is understanding it as 3 b1 3 b1 plus 2 b2. So, what you are saying, he is not able to understand it, He is understanding something else.
No, I guess what he asked is that if you agree on the basis but not agree on the origin, can you still do the transformation? I think that's what he asked.
What?
The original point from two language.
The original point on the two means this is the original point in two language.
No, the origin.
The origin 0 0. Oh, it will be the same because they agree that 0 0 is the 0 0. Like 0 length is 0 length in any scale, right? Okay. The origin is same. That's why I draw it like this. Okay. So now how to do it? So one way to think of is you think of this like his system is a transform system, and whatever the point I have, I apply the transformation to this system. Okay. Is that clear? So now according to you, your basis will move from here to here, right? So there should be some transformation which make your coordinate system exactly like his coordinate system. You can find a transformation which makes your coordinate system exactly like his coordinate system. That is the first thing you have to do. So what will be this transformation? How you find this transformation? It's very simple. This transformation will be the location of the new basis, right? So what is the location of the new basis? It's like 2 1 and minus 1 1. So this is the transformation, simple. Yes or no? So this transformation will transform your basis to the new basis. Clear? Any doubt up to this point? So it will, what it will do is it will rotate your system and scale it according to the system of the alien. Okay? No?
I just slept a little bit.
Okay. It's okay. So what I do is, what I tell is like, now you have to find a transformation which can take your coordinate system and make it exactly same as the alien coordinate system. That you can find, right? And how to find it? You just have to find the basis vector in your own coordinate system. So this is the B1 in ij system and B2 in ij system. Okay. So if you are able to find this, you can simply align them as the column, and this is the transformation that transform your basis to the new basis. Half of the work is done, right? Now you are in the new basis. Is it clear? So now whatever you do is, whatever the point that he says, if he says 5 3, okay, 5 3 and 1 3, suppose he say this. So if he says 5 3 and 1 3, right, or you say 3 2, suppose. So your point was 3 2, you want to transform it to the new basis. So what you do is just multiply with this transformation, which is 2 minus 1 1 1, right? And whatever you get, you will get the where this point will move. Okay, but this will tell you what is the new location of this point in this transform axis, right? It will not tell you where, it will not keep the point fixed. There are two different things, that is what I mean. It will rotate this, not keep the point at the same location. You want the point to be the same location, don't rotate the point, but rotate only the axis. But if you do this, it will even rotate the point, it will tell you the location of this point in the new. Do you get me? What is the difference?
So location of this point in his coordinate system.
Yes. So how this point will go to his coordinate system? That is what this tell you. Do you get me what I mean? Is it clear up to this point?
Now I'm not clear about if we use this transformation, when we multiply by the original vector,
Okay, so let me take an example, I think it's better. Suppose you take a vector as -1 and 2. Suppose you take this vector. Okay. Yes. No, this vector is described by this system. Okay. This is the point given to you by the alien. So these are the point in his space. Okay. Now you want to find out what this mean in your system. Is it clear up to this statement? So the alien tells you, in my coordinate system the points of a vector are -1 and 2. Okay. Is it clear? So what does he mean by this? He simply means by this is the v vector is, according to him it will be like, because he is doing according to taking the basis 1 0 and 0 1, right. So these are the coordinates based on his local basis, but because you know how the axis get transformed, so you can easily find it. So according to you the v vector will be simply -1 times, because this x axis, what is this b? 2 1 plus 2 times -1 1. So according to you, if you solve this equation, you will get the location of this point in your basis, because it's just the linear combination of these two. Like for him, what this point is the linear combination of these two, and this linear combination does not change if you go to any other system, right. That is what we learned. The linear combination is always the same, right. So in your system, if I say in my system, if I add this and this with some scaling, I get this point, right. That is what I am doing here. Is it clear or is it not clear? Okay. In your system, so you remember this diagram. Now forget about everything about what alien says. Okay. So what you do is, alien says that I am constructing a vector by linear combination of two vectors. That is what alien is saying. Alien is saying is that I am constructing a vector which is for this is -1 times b1 plus 2 times b2. This is my vector v, right. This is the vector given by the alien, right. But for him, the only problem that you face is, for him the b1 and b2 are different from what you have the b1 and b2, right. That is the only problem. So a simple solution is, represent this b1 in terms of your language, represent this b2 in terms of your language, and it will solve the problem. Yes, this is what the alien says, right. Like this is what the alien says, right. So the only thing you have to do is represent b1 in your language, that is all you have to do, b2 in your language.
It's just like you try to describe mango in Thai and in Chinese.
Yes, similar to like that.
Yeah.
So you just use your own language or use your own words, that's all. Yes.
In both languages.
Same, yes.
So that's an exception.
Yes. For them the axis matches. Okay, so is this clear? So if you solve this, it will be how much? -4 and 1. So -1 2 in his coordinate system is 4 1 in your coordinate system. Can you calculate this? -4 and -4 and 1. So let us take an example. I think it's better if you. So just transform this point.
I think it's -4 and 0.
No, it's 2 times 1 and -1 times 1. Just transform this point in your system. Solve this in your system. Solve. So this is what alien tells you. In his system, the coordinates are 3 0. Tell this in your system. What is this in your system? So what are the possible answers? What you get? So Sampur says 6 3. Any other answer? Any other answer? Who says 6-3? Who says 6-3? Any other answer? Can you calculate? Can you calculate it? You don't understand. Okay. I said that the alien says that in my coordinate system the point is 3-0. What will be this point in your coordinate system? So you plug this in this formula and you know B1 is 2-1, B2 is -1-1 in your coordinate system. So just plug it here, means this is A, B and okay, whatever. Do you understand what I mean to say? So that is how you get the transformation like that what this point means from his coordinate system to your coordinate system. That is what you want to find out. 6-3. So who gets 6-3? Please raise your hand. Raise your hand who gets 6-3. It's a very simple example. 1, 2, 3. Everyone gets 6-3. Okay, who don't get the 6-3, raise your hand. Okay, so it's a very simple example, right? How to change between the two bases. Yes, but there is a how say in general if you have a point xy, what you do is, let us take a general example. So suppose B1 is represented by say AB, B2 is represented by CD, and this representation is in your system. Okay, I am saying this is the representation of these two basis vector in your system. Okay, so any point x y in say other system will be represented by x times AB plus y times CD, right? Yes or no? And if you solve this, it will be XA plus YC and XB plus YD, and this is just like the matrix vector A, B, C, D, X and Y, right? You just have to transform it. So just if you need the transformation as exists, you can calculate the transformation of any points. You just have to multiply with this matrix, the matrix of the basis of the new system in your system. What is AB? Is the basis in your system for the first axis. BCD is the basis in your system, like the new basis in your system. Like you arrange them in the column and so on. Is it clear?
This vector V is the basis.
No, vector V is the location is the location in your
New basis.
location in your system. So I say x prime or y prime, something like this I can say. So let me say, so xy is in another system, x prime, y prime is in your system.
It is a basis in your system.
No, not basis, the vector in my system.
And
So what he, okay, so let us explain from the start.
this A, C, A, B, C, D, this is a basis transformation.
Is the basis transformation. How the first basis of that is transformed.
That they transform the new basis to the old basis. Transform old basis to the new basis. It means that
You will not get the basis, you will get the vector.
it's our basis.
You will get the vector. If okay, if you take okay, oh I know what he means, but the point is these are the transform bases, but this is the point in point represented in his basis. X, y is the, suppose he give you a coordinate, suppose the alien gives you 5, 2. What does it mean? He mean 5, 2 with respect to his basis.
5, 2 is mean the component of the vector.
5, 2 is the component of the vector.
It's transformed. Like
No, 5, 2 is the component, like if I say 3, 2 is the vector, right? So, if he gives you x, y, it is the component of the vector in his basis.
I think the component of the vector is transformed, not like the basis transform.
No, no, it's not like, it's the same point.
Yeah, it is the same point.
But how the point is represented in your coordinate system. Like I say, the picture that I draw is like this, right? The point is same, but according to him it's like,
Yeah, I think we have to transform. We have two transformation
Huh?
in this case. It's mean that we need to transform basis first, and if we transform basis first, and the location is transformed.
no, no, no.
หมายถึงไม่ใช่ทานอย่างนั้น
Trans.
It's so he Pradeep is going to no he has already put the new basis
Yes,
described in the whole
basis.
That's not transformation.
That's not transformation.
From that he defined the transformation. มีการ transform ครั้งเดียวตอนนี้ sorry let me เขาเนี่ยนิยามเวกเตอร์ใหม่ขึ้นมาแล้วที่เป็นเวกเตอร์ของฐานใหม่ซึ่ง describe ในสเปซของฐานเก่าแล้วเขาใช้ในทำ transformation matrix ที่เขา transform อยู่ตอนนี้คือtransform จุด x y ใดๆไปยัง x ตามไปทำมันใหม่ก็นั่นเองมีครั้งเดียวเท่านั้น just one transformation.
I think intuitively it's very good to understand it. Okay. What is x, y? Oh, okay. What is x, y in his basis? What is x, y in his basis? X, y is just a linear combination of B1 and B2. Think about all the coordinate system, remove everything about. What is x, y? If he says x, y, what he means x B1 plus y B2, right? That is what all he means. If he say x, y, this is what he mean, right? And this is also what you mean. Both have the same thing, right? If he say x, the only thing that is different is for him the B1 is 0, 1, for you the B1 is AB. That is the only difference you have. Do you understand now?
If I understand is we
Oh,
need
sorry, 1,
to
0.
transform 0, 1 to A.
No, you don't need to transform. So if he say that a point is this is the point AB, x, y is the point, what he means? Okay, forget about everything. Let us if I say a coordinate system, if I say 2, 3, this point, what does I mean? I mean 2i plus 3j cap, right? That is what I mean.
Yes.
If I use any other system, suppose B1 and B2, if I have this point, say 3, 4, what I mean? I mean 3 B1 plus 4 B2, right? This is what I mean. Yes or no? So if he says this is what he mean, right? For him the definition of B1 and B2 may be different from what your definition of B1 and B2 are.
Okay.
That is the only difference.
I understand this one, but they not
Okay.
get this transformation.
Okay, so for him this is what he mean, right? Or more precisely, let me do it like this.
So I understand this one, but I not understand this. You do like an
This-
extra y function.
Okay, that is what I'm saying. So for him x, y is his coordinates. X, y is the coordinate that he mentioned. Okay, the coordinate respect to the B1 and B2 for him, not according to you. Okay, do you understand it, what I mean? So what this means is he is define a vector which is the linear combination of the two vectors. That is what he defining here. He defining what this means. This is a linear combination of two vectors. Okay, now you have to find out what is this vector. If you add two vectors, it may not be the same coefficients. Okay, you just have to find out what is this vector. The coordinate of this vector is x, y, y prime. So he only says that, what he tells you, he only says that I take B1 vector with some scaling and I add them together, then I reach one point. That is what tells you. Forget about x and y. Do you understand what I mean to say?
Can I help
Yes, you can help.
translate?
Yes.
โอเคมันติดคอนั่นแหละ translate คืออย่างนี้จริงๆมันเรื่องมันง่ายนิดเดียวคือว่าตอนแรกเนี่ยประทีปเนี่ยเขากำหนดมาให้ก่อนเลยว่าอันใหม่เนี่ยนิยามก็เป็นยังไงแล้วหลังจากนั้นเนี่ยพออันเวกเตอร์ฐานอันใหม่เนี่ยนิยามโดยโคเนตของอันเก่ายังไงพอได้ซึ่งเขาจะให้ B1 แล้วก็ AB กับ B2 แล้ว CD AB กับ CD เนี่ยพูดในฐานในกรอบ S S ปลายแล้วเขาก็มาสร้าง transformation matrix ABCD ใช่ไหมฉะนั้นเขาจะแปลงจุดใดๆ x y ใดๆในโคเนตเก่าไปเป็นจุด x y x พลังกับพลังเป็นอะไรเขาใช้ transformation matrix นี้แล้วไอ้สิ่งเนี้ยถ้าเขาจะใช้ transformation 0 1 เป็น0พื้นฐานไปทางโน้นแล้วเขาก็ทำได้คือเขาtransform ไปทางเดียวจริงๆมันเรื่องมีแค่นี้เองแต่เขากลัวเราไม่เข้าใจเขาเลยพูดซ้ำอยู่นั่นแหละคือตอนเนี้ยเขาเนี่ยคอนเซิร์นกับพวกนายมากเขาเลยพูดซ้ำจนกระทั่งพวกเรางงเอง
So the same point, but for alien this is what he mean and this is what you mean. That is all I am saying. It's the same point.
It should definitely x and y. It must be.
No, it's not. Don't use same different x and y because for him is the basis vector, but for you it is the combination of two vectors. Because how you define your coordinates based on not these vectors, your coordinate based on, so it will be different x prime on 1 0 plus some y prime on 0 1. Do you get me what I mean? If you write it in terms of 1 0 and 0 1, you will get some x prime and y prime. That is your coordinates. This x and y are the coordinate in this system.
So you have a basis vector in the Newtonian.
Yes. Yes. So this is his basis. This is B1 and B2. According to the B1, so what he tells you, he does not tell you about coordinate system. He tells you about that I take these two vectors and they take the linear combination of them. Then I reach some point. You just take this information. You don't care about what his basis vector are. Okay. You are not making any transformation here. You are just representing what information he has into your own information. That is all you are doing. There is no transformation. But there is a way to think of it as a transformation. You can think of this as a transformation. Okay. But there is no transformation is happening here. It's just representing the same information from the old set to the new set. Okay. It's not like exactly a transformation, but you can think of it as, okay, one thing I can do is I can move everything to his system and then see the point, how the point get transformed. That is a way to think of it. But there is, so usually transformations transform the space. You are not transforming anything. Like I say that the point is here. Okay. The point will always be here. It's only how you see it and how, like for example, is the same way of saying is like for you the bottle is 2 centimeter apart, for me is 5 centimeter apart, because we are using two different reference frame. So that is what he is saying. For him the reference frame is x and y, how far it is from him. Suppose he sits at the origin, he treats his position as the origin. So for him the bottle is 2 centimeter apart, for me is 3 centimeter apart, right. So how we find out? We find out how far you are from me and how far the bottle is from you. If you add up these two, you can get the bottle, right. So it's the same way I am doing. How far these vectors are from my basis, my axis, and then add them together, I get where the point I will end up with. I think we can discuss it maybe later. Okay. Now let us do. So this is a simple point transformation, but how can I understand the transformation in his language to my language? Suppose he transforms his coordinate system by 90 degree. So his coordinate system was B1 and B2. He again rotated it by 90 degree. So how do you understand that? It's bit, and it's very simple to understand it. It's not. If you follow the physical, I think it's very easy to understand. Suppose I use in my representation I use this transformation. What is this transformation? It's a 90-degree rotation, right? And this is in our basis we represent this transformation, not his basis. Okay. Now how to find out what will this effect has is on his coordinate system. Okay. So how to do it? Suppose I have any vector, say -1 and 2 in this vector is in x basis. X basis means the other basis, the alien basis. Okay. So it's similar way of saying that he tells you this x and y. So this -1 and 2 are this x and y. Okay, not x prime and y prime. I'm not saying about x prime and y prime. I'm saying only x and y. Okay, is it clear? So what I do is I change this vector in our language. So in our language the vector will be if I use the same example before. So in my case, in that case 2 1 -1 and 1 was my transformation that transformed the basis. Yes. No, this is the transformation that I apply to full space. This is the transformation which transform my axis to his axis. Okay. This is are these A, B and C, D. So A is this one and C, D is this one, right? This one. Do you get me what I mean? So this is how I represent one point in his coordinate system to my coordinate system. Okay, so it will be represented by this matrix which is or maybe T times, say this maybe I call this as x vector. T times x is, so x is in the alien basis, right? It's better to write in alien basis. T times x is in my basis, the same vector. Is it clear? Because I change my coordinate system according to that. So I align my coordinate system, T will align my coordinate system to his coordinate system, and if I multiply with it, I will get the transformation back. Okay. Is it clear? Now in my coordinate system I apply this this rotation which is RTX. So RTX is the rotation in my basis, how my point moves to, because this is my point, right? And if I again multiply with T inverse, it will be again in his basis, right? Because T takes his point in my basis, T inverse take my point in his basis, right? So you can combine the matrices accordingly. So if he give you some point, you first transform this point to your basis which is Tx. Now on this point, because you have the transformation in your basis, so you apply the transformation and again convert it to in his basis. That is all you have to do. Clear? Not too clear. So let me, because it's only 1 hour left.
I'm a janitor.
So let me ask you one thing. Do you want me to go into the mathematical definition of vector spaces or not, or you want me to do something more physical like the eigenvalues and eigenvectors and the spaces and like how you can use this information to do something meaningful, like what are the application of these techniques? I can go into the mathematical definitions which Thiti want me to go. So what you want me to do? The same way or you want some mathematical?
Some but not many times.
Okay. Okay.
But not many time repeat.
Okay. So,
Essential code.
so let me briefly define the mathematical things, the vector spaces. You want me to define the vector spaces or not?
Can you define dual space?
Dual space? No, I have not defined it, but
We not define dual space?
we don't define it. Oh, I think my notes are gone. Let me find out my notes. So now I'll briefly define the vector spaces, and then I'll move to maybe the physical concepts of the eigenvalue eigenvectors. That is most important, which you use, at least for physicists, you use it in your like most of the calculations. Okay. So let me go to the vector spaces. Yes. So before vector spaces, you have to define field, right?
Field?
Yes.
Okay. Field.
Not you want to
The mathematical field,
yes, the mathematical field.
not physics
Yes.
field.
Okay. So let me define a field. So this is not like the magnetic field or the
We need a field or we need a ring actually.
yeah, you can do one, but I think the field is the more basic that I should.
Oh, okay. I'm not sure, so I ask you.
So field is simply a set along with two and I define this operation as plus and sorry, my board work is very bad. So I define the field. Such field is a set along with the two operations which you defined as the addition and the multiplication, such that certain axioms hold. So first of the axioms is first there is a closure. Closure means if they are elements A and B, so A plus B should be a member of whatever you call in F, A dot B should be in F, okay, for any member A and this is the closure defined. If A and B are in F, any two members of this set, so the sum should be in the result of the sum should be in the set and the product should also be in the set. That is the first. The second thing is associativity. So I'll just write it. So A plus B plus C should be equal to A plus. Okay. The third is it should be commutative. A plus B should be equal to B plus A over addition and multiplication. So what I mean is, for multiplication it will be A dot B dot C should be equal to A dot B dot C and A dot B should be equal to B dot A. Okay. And there should be the identity such that if I add something to A, it should be A. So that identity is 0. So 0 plus A is equal to A, and for multiplication it is 1 dot A equal to A, right. And there is a concept of the inverse, so that if I add something to A, it should give you a 0, right. That is the additive inverse. So A plus minus A should be equal to 0. Okay. And similarly for the multiplicative inverse, it should be A times A inverse should be equal to 1, something like that, which is the reciprocal in some sense. Okay. And the last property is distributive over the multiplication and the addition. So you define it like A dot B plus C should be equal to A dot B plus A dot C. So very simple properties, right? You always encounter these. So this is if a set satisfies these conditions, you call this as a field. That is what this means. Okay, it's a very mathematical definition. I don't know how to physically represent it, but you assume that they are set of numbers which satisfy these properties, and you call this as a field. Okay. Is it clear? And the vector space that we call, because all the vectors are the member of the vector space, that is the basic definition. We said that these vectors, they lie in certain space which we call as the vector space. Okay. What does this vector space means? That is what we are going to define mathematically. Okay. So in generally when we say vector spaces, like we say that the space should be closed under vector addition and the scalar multiplication and so on. There are certain axioms that has to be satisfied. So the basic definition is, suppose you have a vector space which we call is a vector space is a non-empty set V. Okay. So you have a non-empty set V, and this V, the elements of this set V, we call them as vectors. Okay. And then we define this vector space over some field F, which is the field of scalars. Okay. And with the two operations which are the addition along with addition and scalar multiplication. Okay. So these are the four things that we define. We define a non-empty set, we define a field of scalars, and we define two operations, which is the vector addition and the scalar multiplication. Okay. And if this set satisfies certain conditions, just like those conditions, then we call that this is a vector space mathematically. Okay. So what are the conditions? So let us say, suppose u vector, v vector and w vectors are in V and alpha beta are in F. Okay. So the first condition is it should be closure. The vector addition and the scalar multiplication should give you a vector which is inside the space. Okay.
So you're saying vector space is a non-empty set V
yes.
belong to the field?
No. So along with the field.
Along with the field.
Yes, and two operations. So this vector space is defined along with the field and with these two. So we say that this vector space is over the field F.
So yeah. So basically the numbers we see in the vector have to belong to the field.
Field F.
Yes.
So when I define this like 2, 3, these numbers, they belong to F. Like the real numbers, you can say, whatever we define, the set of real numbers and so. Okay. So the first thing is u plus v vector is in V or is in capital V. Okay. Second, a u vector is in V. Okay. Because whatever you do to these two operations, you should not go out of the set. You should be within the space. Okay. Then all these properties like u vector plus v vector plus w vector right. So 2, 3 and 4, there exists a 0, there exists a 0 vector such that u vector plus 0 vector is u vector, right. This is additive identity, right. The 5/5 is scalar multiplication distributive. Okay. Oh, it should be the one is the fifth one is u plus v vector should be equal to v vector plus u vector. This is fifth. Then the sixth one should be the inverse of so for each v, for each u vector in V, there exists a minus u vector in V such that u vector plus minus u vector gives you the 0 vector. ST is such that if you don't understand, and this is there exist, if I am writing making the correct sign or not. So this symbol is there exist. Okay. Then you have alpha of u vector plus v vector is alpha u vector plus alpha v vector. 6, this is 7th. There are a total of 10. 8 alpha plus beta of u vector is alpha u vector plus beta u vector. Oh, alpha beta u vector. Then 9th is alpha beta u vector is equal to alpha beta of u vector. And the 10th is there exists identity such that I vector times u vector is u vector. Or maybe oh no, oh yes, maybe last. I don't know how to represent this identity, but
Do we need number 8 and number 7?
do we need number 8 and number 7? Yes.
Don't you get it for free because
Wow.
alpha and beta belong to field?
Yeah, alpha and beta belong to field. Yes, you get it for free. But this is the recursive. Well, like you define it.
Yeah, but you already say it belongs to field.
Yes.
So don't you get it for free?
Yeah, you can get it for free. But the point is, in one case, it is this simply means the vector scaling.
Yeah, but I mean like.
No, this is obvious.
Yeah,
But
no,
if
not now, but I mean 8. 7 and 8. 7 and 8.
Why?
You should get it for free, right?
Why? Because it's distributed over the vector multiplication, not distributed over normal multiplication. It is the vector multiplication. It's distributed over vector multiplication. There is no vector multiplication here. So the vector multiplication is different from the normal multiplication, right? You have to scale both the elements of the vector or all the elements of the vector. You have to define the scalar multiplication. So that is what is defined here. So that's why you needed them. I want to define the subspace, but let's forget about it. There is no time. Anyway, you'll not do it.
The identity, this identity have to be vectors?
Oh, it may not be. Yes, you can remove this, but you can treat it as 1 1. Basically 1 1.
No.
Yes.
I don't know, is that question or what? Why we don't define 0 multiply A?
0 multiply A because it will be 0.
Yes, but it's obvious, but like a 0 plus A equals.
Because this is the identity over addition. We define, so two things we define. We define one is the identity. So identity can be defined over addition or over multiplication. So over addition means if you add something to that number, it will still be the same number. Yes. And multiplication means if you multiply something with that number, it will be the same number.
And how about 0 multiply A?
Okay. So then you can define something called as the inverse. We don't define 0. We don't define 0. We define only identity and the inverse. Inverse over addition and inverse over multiplication. These are the only 4 things that we define. We don't define 0. That is not required within the field, because 0 is always contained here. You will always, not the same 0, but in some sense the notion of 0 will be there. So, you do not need to define 0, because this already defines 0, and you do not need to define. So, if you say you want to define 0 times a is equal to 0, you also have to define 1 times a equal to a, 2 times a equal to 2a, you define that. But that is the outcome. You can generate them from some of these.
What about the book I learned it, that give us 10 properties of a vector space, but then without saying that the scalar and the field, but they just remove it. They just say there's a scalar, and they give you exactly the same 10.
Yes, but this is always our field. You have to define a field first.
The identity is in the field.
Identity, no, not necessarily. For example, here 0 vector is the identity. On the 10, the identity may be, you can define, it may be over the field or over the vector. Do you get me what I mean? How I say it? You can define a.
We have the vector multiplication.
Yeah, we have the vector multiplication. Means you only have scalar multiplication. You don't have the vector. So it should be over the scalar. It should not be over the, because I do. So far, I have not defined the vector multiplication. Okay, it should be over the field. But what I mean to say is, there are other higher elements of the identity. Like you can have the identity matrix, which you can multiply with the vector, you can get. Okay, do you get me what I mean? So, from, let's forget about this. Should I erase this? Okay, I'll remove this. Let me go to little bit mathematical, and then I'll go. Most important thing that I want to cover is, so I already discussed you that the linear transformation, we can discuss it with the help of how say, with as a column of a matrix, right? Yes. So, any question?
So it will be nice to say that for each you can just put the mathematical symbol, like
Yes.
the reverse A. For each,
Yes. For each?
it's like reverse A. Like
Yes.
For all.
Yes.
Yeah,
For all.
For all.
Yes.
For the axis is for some.
For all. So their axis is like this.
Yeah. I think
Okay. Yes. Okay.
get that.
Yes. Because if sometime I feel that.
You have to complete both.
Yes. Okay.
Symbol for such term.
Oh, there is no symbol, I guess. At least I don't know it. At least I don't know whether anyone knows the symbol for such that. I don't, maybe Thiti might know it.
I just know for each is for all, and the reverse E is for some. The axis only. No, the axis means some. There's something exists there. But for each, that means for all of them. For all. It's like that. We and it's like A, but then A like that.
So let us move to the.
Thank you. That's a good lecture.
No, let us go to the eigenvector and eigenvalues. I think that is the last topic that I want to cover.
Thank you.
If you want to leave, you can. If you want to kill me, you can kill me after that. Then I will be satisfied that at least I completed. I extracted my revenge. Okay. So last thing I told you that there are certain matrices which just rescale the axis, right? Suppose I take a matrix which is maybe 3 0 0 2. So what does this transformation do? It just rescale two x's, right? But there are other form of matrices which is very very important. So so in this case what will happen? You will always be in the 2D space in the same direction, only your how say, only your rescaling will be there, right? Okay. So if I take any vector which is to this say a b, so this vector will become 3a and 2b or something like that, right? Okay. So this vector get rescaled. But suppose I do a very special kind of matrix. Let me take an example like 3 1 0 2. Okay. So this transformation does not do anything to the x axis, but it changes the y axis, and I take this vector minus 1 and 1, minus 1 and 1. Okay. So what I will get? Can you solve this? Minus 2 and 2, right? So I can write this as 2 minus 1 and 1, right? This is different from this. In first case, although both the axes of the vectors get rescaled independently of each other, right? In the second case, the vectors get rescaled by itself, right? So if you encounter any such scenario, what it means that there is no change in the vector. The directionality of the vector does not change, only the scale changes. And whenever you counter these kind of scenario, you say that this is a eigenvector of this matrix and the rescaling is the eigenvalue. That is only the physical significance of eigenvalue and eigenvector. So you take a matrix, you apply on a vector, and if the vector does not change, it is an eigenvector. It does not change the direction, it is only change the scaling. Then you say that it is an eigenvector, and the rescaling that it does, how big or small it makes this vector, that is the eigenvalue. Okay? That is a very basic concept of the eigenvalue. So in general, if I represent this transformation A, this vector as V, so you will get something called as lambda V, right? This is how you mathematically, in general you mathematically represent it. AV is equal to lambda V, because it is the same VV and there is some lambda is some scalar. Okay. It can be complex, but let us move to assume that it is a real scalar. Okay. So now you can write this as AV minus lambda V equal to 0, right? And in order to solve, because you have to find out how many lambdas are there, right? How many values can this equation satisfy? There will be many possible lambdas, right? So for all these you have to take the determinant of it and solve it. So you will find a characteristic polynomial. If you solve that polynomial, you will get different roots of this equation. It may be 2 by 2, like for example in 2 by 2 matrix you will find 2 eigenvalues, right? They may be the same eigenvalue or may be different, and whatever, one may be 0, one may not be 0, and so on. Okay. So one important things to note, suppose I take any matrix, say 4 5 3 2 some xy, and I get the eigenvalue 0, I get the 0 vector. This is a very special case, right? So this is mapping it to a 0 vector, which is simply like the null space. Null space we define, like it takes the vector and take it to the origin, take the vector, make the vector to be the 0 vector, right? In this case you can say that, you can write this as 0 times x and y. So you say that the eigenvalue is 0. What does this simply means physically? This simply means that this direction is not important. You can represent this direction as the linear combination of the other directions, right. So, this direction is not an independent direction. So, eigenvalue 0 simply gives you that there is something in this direction which can be represented as a combination of the other directions. Okay. So, the non-zero eigenvalue of the systems are actually the independent direction that you can choose, which represents which can exactly represent your system. Suppose you have a 4-dimensional system, okay, or 4-dimensional transformation, 4 by 4 matrix. It can have at most 4 eigenvalues, right?
Yes.
It will have 4 lambdas, lambda 1, lambda 2, lambda 3, lambda 4, right? If suppose 3 of the lambdas are 0, so it essentially tells you this transformation is a only 1-dimensional transformation. It maps everything to 1 dimension. Yes or no? Because you can represent this just by looking at the eigenvalues, because all 3 the vectors in all 3 directions get mapped to the 0 vector, right, to the null vector.
Can you repeat when you say 0 eigenvalue?
So suppose these 3's are 0, only one eigenvalue is not 0. So it means that there is only one direction in which you can take the measurement. In the other direction the measurements are 0.
Okay, suppose that all of them
Are 0. So it means the full space is mapped to the 0 or the origin.
0 what?
Full space is mapped to the origin,
Origin.
the point.
Okay.
Like whatever the 3-dimensional or 4-dimensional spaces, you crunch everything to the origin. That is what it means in physical sense. Yes, is it clear? So the number of non-zero eigenvalues, the first thing that it tells you that what are the independent, or what is the basis of your number of bases your system has, or what is your independent, or what is the dimensionality of your system exactly, what is the dimensionality of your of this, after this transformation what will be the dimensionality, in which dimension you will land it. Okay. Do you get it? So you can map every vector to certain dimensions. You can go from higher to lower dimension, and that is very useful when you want to check whether in your data if there is some degeneracy or not. A simple example you can think of is like suppose you have a simple pendulum, right, spring mass system suppose you have. So you know it's only a 1 degree freedom system, right, it only has 1 degree of freedom. You can exactly map it by change, like recording its length. What is the change in length? L dot will tell you everything about what is happening to the system, right. But suppose I do an experiment, I take this like this and I make it like this, and I make x and y observations, but I have 2 observations, not 1, right. So I will have observation on x and observation of y, something like that, right. So is it a 1-dimensional system or 2-dimensional system? You cannot say just by looking at x and y values, right. Is it clear? Because it's very simple, you can somehow find out by plotting, you can find out that it's a straight line and so on. But in general, for any system, if it is a very big system, you cannot find out whether there is some degeneracy in the system or not. You can measure, like for a system, you can measure 10 different properties, but you are not sure whether each of these properties is important or not. Yes or no? You can measure anything. For example, a particle, you can measure its weight, charge, height, where it's going, x, y, z or whatever. Like for example, I take you the example of this university. You can measure its students, the fees, the curriculum or whatever you want to measure. But the point is all these observations independent of each other or not? That is what the eigenvalues and eigenvectors are important. So what you do, you take this observation, and what you do is you calculate the correlation between these two. You get a correlation matrix which will be the 2 by 2 matrix. So this 2 by 2 matrix will be the correlation between x and x, correlation between x and y, correlation between y and x, and correlation or maybe y and y, something like that. You can whatever you want towards. So it's a 2 by 2 matrix, right? Now calculate the eigenvalues of this correlation matrix. You will find that the one eigenvalue will be non-zero and the other eigenvalue will be 0, because it's a 2 by 2 matrix. or let me do it in 3D. I do a spring mass system, I observe x, y and z coordinates. So my correlation matrix, so the observation will x, y and z, right. I will have 3 observations, one for this spring mass system how the x is changing, for this mass system how y is changing, and align this like the diagonally of this room. So I record all 3 observations. So there will be some finite value of x, some finite value of y, some finite value of z, right. If I align diagonally like this, so all 3's are changing. So I record all 3, I calculate the correlation matrix. That is the first thing I do. So this is the correlation between x and x, correlation between xy, correlation between xz, correlation between yx, yy. Okay, so I have 9 elements which represent all the possible combination of the correlations, right. Now you calculate the eigenvalue of this correlation matrix, and this correlation matrix will, the element will be, the diagonal will be 1 and some other values which will be there which are non-diagonal, and the other values which will be between -1 to 1, right, because the minimum correlation is -1, the maximum is +1. Is it clear? I hope you know the correlation. You know correlation? Okay. This is simply, you have sigma x, sigma y. You can, this is, I do not have to take these, and this is correlation between x and y. So simply what you do is, you take each observation, subtract its mean, multiply with another one, okay, and take the mean of both, something like that. I think you will, that is the formula, but I am not sure whether I should explain it in detail, because we are already out of time. I want to cover some more things, okay. So the point is, you transform it as a correlation matrix, and from this you calculate the eigenvalues. That is a very simple thing that you can calculate. You have a matrix, calculate eigenvalues. So you will find that lambda 1 is non-zero, lambda 2 equal to lambda 3 equal to 0. So you will get only one eigenvalue, right. What this tells you? This tells you that your system is a one-dimensional system without doing anything. You have not done anything. So for any observation that you get, suppose you get, for a system you get 10 observations, 10 different variables. The first thing that you should do is calculate the correlation matrix, find out the eigenvalues, and you will find out what is the exact dimensionality of your system. That is the first thing that you can do without doing anything, to find out the exact dimensionality of the system, okay. Now the second thing comes out, okay, I find, and numerically what will happen is, all the eigenvalues will not, this is the ideal case where the eigenvalue will be 0, but if you have very long matrix, there is some like computational error, so eigenvalues will be like lambda 2 will be like 10 to the power minus 40. It is non-zero still, but you can assume that safely that it is 0, right, because it is a very low value, because mathematically or computationally when you calculate it, it is always non-zero, because there is an algorithm that the computer program use, it use some rounding off, so it will not be mostly 0, but computationally this problem occurs, but that is the first thing, okay. Now the second thing is, suppose you have a very big system, suppose I have a 50 variables for a system, and 50 variables are too much for you to like analyze together, right, and you want to take this 50 variable system and do it to 3-dimensional system. So what you want to do is, you have a system with 50 dimensions, means 50 dimension, what I mean in data sciences, you have observation x1 variable, x2, x3 up to x50, okay. So you have this 50-dimensional system, okay, and you want to reduce it into a 3-dimensional system. How to do it without losing too much information, okay. So what you do is, you take the correlation of these 50, which will be 50 by 50, okay. So from this 50 you calculate the eigenvalues, suppose lambda 1 is greater than, right, you arrange them according to this fashion and you only take 3 eigenvalues and the corresponding eigenvector. Okay. So, what this tells you? This tells you that the lambda 1, which is the largest eigenvalue, the corresponding, if I align my system in the direction of the corresponding eigenvector, I will get the maximum variance. My system expresses most in terms of this E1, second it expresses in terms of E2, and third in terms of E3, and this is the basis of the principal component analysis. These are known as the principal components. The first principal component is the direction in which you have the maximum variance in the system. If you align, like you make a transformation so that your system now moved into a direction in which the largest eigenvector, the x axis is the largest eigenvector, y axis is the second largest, and z axis is the third largest, and you discard all other dimension. You will still be able to explain almost 90, like in general case almost 90% of your system properties, just going from 50 to 3D without any losing of the information, and that is what the basic thing that you do in the principal component analysis. Okay. Second thing, you can transform your system to a higher dimension to a lower dimension using the singular value decomposition and so on. I think that is the basic thing. If you want in your research that you have a very big system, you want to reduce it into a smaller system without losing too much information, you can use principal component or singular value decomposition. That is the best way you can, like that is the change in the space from a higher dimensional to a lower dimension. So far what we have studied before is we only change the rotation or the scaling of the system, right, but you can use a non square matrix to change your dimension. If I align these 3 eigenvectors and transform my data using these 3, so I will be move into a 3-dimensional space. This will be my transformation. Do you get me what I mean? So, this vector, if I use this vector as a transformation of my original data, so I will move into a 3-dimensional space, right. So, I am projecting everything into these 3 dimensions, and that is the crunching of the space. That is what you are doing, is you are making the other vectors, other direction to be the null vectors. Okay. So, you are essentially reducing their effects, you are making them like. So, I think that is all for today. I think I am ran out of time. If you want me to continue, I can continue more, but I think it's okay. I think it's always, I am already over time little bit more.